Hello, everyone. Welcome back to the Stanford HAI Fall Conference on Triangulating Intelligence, Melding Neuroscience, Psychology, and AI. We had great talks and discussion this morning and are ready for our next lineup of super speakers for the afternoon. I'd like to remind everyone that you can submit questions for any of our speakers on the event page on our website down that right column where there's both opportunities for questions and for just chat comments. And on Twitter, you can use the hashtag #NeuroHAI, NEUROHAI. But without further ado, I'd now like to introduce our first speaker, Sanjeev Arora, Professor of Computer Science at Princeton University. Welcome, Sanjeev. Please unmute yourself and turn your video on, and we're really looking forward to your presentation.
Good afternoon. Today's talk is titled How to Allow Deep Learning on Your Data Without Revealing Your Data. But after some consultation with the organizers, they thought it would be useful to add some thoughts on mathematical understanding of deep learning, which will be the first few minutes of the talk. So this introductory section concerns the ongoing effort towards mathematical understanding of deep learning. And given the complexities of deep learning, you may well wonder if that is the oxymoron of the day. So in the next few slides, I'll try to give you a very brief taste of this growing area and give you 3 reasons or motivations I think it will be essential in the long run. And then in the rest of the talk, I will talk about how to do deep learning on your data without revealing your data. Just to lay all my cards at the table, I believe that at its best, theory should surprise and challenge practitioners instead of just formalizing their entrenched intuitions using some epsilons and deltas. So without further ado, the 3 motivations why we need mathematical understanding of deep learning. Motivation 1, to get very far in AI using deep learning, we need better mathematical understanding of properties of the trained nets. And the main reason we lack such understanding right now is the current black box approach or viewpoint of deep learning. All you need to do deep learning is to settle upon an architecture, define a loss function, and start doing gradient descent on this loss. But we lack any significant insight into what happens during this gradient descent, which in turn means that we lack any insight into the final solution that this gradient descent produces, namely the trained net. In other words, this trained net is a black box to us, and this whole process is a black box to us. Now, if you began to understand something about what gradient descent is doing, you might start getting some of the good stuff that we want, like explainability and interpretability of the net's behavior, and some properties that we can't just verify using held out data, such as robustness to distribution shift or adversarial perturbations, something that some people call strong generalization beyond the training data. And this theory is now starting up. To explain further how the black box view of deep learning is holding us back, let me give you an example. You have all seen language models like GPT-3, which have caused a revolution in natural language processing in recent years. The training loss of these consists of performing well on what you can think of as fill-in-the-blank tasks. The model is given a partial sentence like, Rob went to the cafe and ordered a blank. And it is trained to produce a distribution on missing words that predicts the next word well, such as this distribution like probability of latte is 15%, probability of Danish is 10%, and probability of dog is 0.01%, which is very unlikely. Okay. So I'm assuming you've seen language models before, and the phenomenon I'm interested in is the following: that the same model, which is producing these distributions of next words, is also along the way giving us very powerful semantic representations of text. which are helpful for all kinds of other NLP tasks and revolutionized NLP in recent years. So specifically, when you input this piece of text into the model, its internal workings involve a vector representation of the text. And this vector representation is extremely useful as a representation of the text in dozens of downstream tasks. Now, to a practitioner, this doesn't seem very surprising because, of course, the language model is pretty darn good. And so it makes sense that it must have developed good understanding of the text. But at a mathematical level, this is not clear at all. And for example, one could wonder, why is the representation so broadly useful? Is it something to do with something special about language modeling, this predicting the next word? Or mathematically, it arises from some property of current deep architectures being used? And as you can imagine, one can't make a whole lot of progress on such basic questions, given that deep learning is a black box. So now people are starting to open this black box. And in a recent paper with two students, Nikun Sonshi and Sadika Maladi, which is now an archive, we give a mathematical exploration for why such representations from such models are useful in downstream tasks. And turns out the answer is that both of those are important. The fact that it's language modeling and that it's also a property of gradient descent and local optimality in there. Okay, so that was the first motivation for why we need mathematical understanding of deep learning. The second motivation for mathematical understanding is that, surprisingly enough, deep learning doesn't fit traditional optimization theory, meaning the stuff that we've been taught in courses for decades. Now, this basic optimization theory is something that both theorists and practitioners know, but it turns out that it can be quite misleading when you drill deep down into deep learning. And let me illustrate today by showing that something even as simple as learning rates in optimization behave very differently in today's deep learning than what we learned in optimization classes. So learning rate is this parameter eta in gradient descent. How far do you step in the direction of negative gradient? That's the learning rate or the step size. And the usual classes have taught us that you should start with high learning rate and slowly make it lower. But in a new paper last year, we show that actually this traditional understanding it does not fit today's state-of-the-art deep net models at all. And by state-of-the-art, I mean those that use some form of normalization at layers. So what this paper with grad student Jeon Lee showed was that these state-of-the-art nets can be trained using exponentially increasing learning rate. In other words, at every iteration of gradient descent, you multiply learning rate by 1 plus c for some constant c bigger than 0. Now, all of you know what exponential increase means. So this indeed means, because it's being done at every iteration, that very soon the learning rate is in the millions or trillions. It's gigantic. You're making gigantic steps, but it still works. And the reason we came up with this crazy idea was that we had a mathematical proof that it would work. We were exploring the mathematics of learning rates, and that's what we came up with. We had a proof that existing training can be done with exponential learning rates, and therefore the experiment was natural, and it works. So after this surprise, we continued to explore learning rates and role of learning rates. And in this new paper that we just put on archive, we tackle another widely held belief, which is that, as you see in this figure, the belief is that learning rate needs to start out high and then it slowly should be decayed, and that this is actually not just needed for optimization, but also for good generalization. And the story vaguely is that the loss landscape is non-convex. It has hills and valleys. And this large initial learning rate leads to some kind of a Langevin diffusion process, which is fairly stochastic, and it helps explore this loss landscape, the hills and valleys, and finds a broad valley or minimum. So that's roughly the theory, and In this paper, we show that this intuition is actually also incorrect for state-of-the-art nets. So you don't need large initial learning. So in the previous paper, we show exponentially large learning rates are fine too. And now we're showing that actually you don't need large initial learning rate or large learning rate at all. And it still trains to good accuracy. And we don't find any evidence of this diffusion theory. And in fact, we show that going forward, what we should look at is function spaces. And we start developing a theory for that. Okay, and now the third motivation for why we need a mathematical understanding of deep learning. And this is maybe a little bit speculative. And I'm suggesting here that current learning paradigms may not be sufficient to lead to flexible interactive agents. Okay, so basically the issue is that when you drill deep down, most, if not all machine learning today is relying on the idea that, that you're learning on a fixed distribution of data. Training and test data points are assumed to be independent samples from the same distribution. So we all know that if the distribution then shifts at deployment time, then the learner is not guaranteed to work. Now, a flexible agent has to be able to do all sorts of different tasks, meaning perform well on all sorts of distributions, for which people have invented various paradigms, which I would simplistically describe as distributions on distributions. And you'll see that a lot, I think, in Josh Tenenbaum's talk. So for example, in meta learning, you explicitly think about your learning on a distribution of tasks. In Bayesian frameworks, you're assuming that the parameters of the task distributions are drawn from a prior distribution. So in other words, the paradigm of machine learning needs inputs to come from a fixed distribution, which is the top turtle in this picture. And this top turtle may itself be resting on another turtle, which is another distribution, which in turn may possibly rest on another turtle, which is a distribution, etc. But at the bottom turtle that's holding this all up is some base distribution where you're taking independent samples from a fixed distribution. So that's the dominant paradigm. I'm not saying everybody in the field is doing this. And it's possible that this can get us all the way to flexible interactive agents, but maybe not. And that's what I'm suggesting today. It's quite possible there is a middle position in the debate that maybe this paradigm doesn't capture intelligence when training data is limited, as it is for humans, but maybe it does it for machines since they can learn from orders of magnitude more data. So I'm open about this, but I'm just suggesting that maybe we need a new paradigm. Okay, so that was the initial part of the talk, why we need mathematical understanding of deep learning. And now I will get to the main part of the talk, which is how to allow deep learning on your data without revealing your data. And this is joint work with this team, grad student Yangsibo Huang, colleague Danqi Chen, postdoc Zhao Sang, colleague Kai Li. And the first paper appeared at ICML, and all the authors except Danqi. And the second paper will be appearing in ENLP findings, and it includes Danqi. Okay, and I hope that this work illustrates what I said at the beginning of the talk, that where I hope theory can be useful is by being inspiring and thought-provoking, coming up with radically new solutions, rather than merely solidifying existing practice. Okay, so today's broader topic is artificial intelligence. And it is clear that in the near future, it's not due to androids or robots of movies, but the devices that surround us. And these devices that surround us are based upon a Faustian bargain, if you will, that we have to hand over our data to a handful of dominant companies, and then we'll enjoy a world customized for you. Now, this raises a fundamental question about privacy, which was in the title, which sounds oxymoronic. How can deep learning be done on my data without revealing my data? But that is indeed the question we'll talk about, that there's all these forms of data that we are interested in that's going to be input into the deep net, and the training here, which is this little hardworking blue man, is doing all this stuff, gradient and backprop through the deep net. and we want deep learning to be done on our data without making us reveal the data. And some of the candidate applications you can think of are, for example, hospitals want to train deep nets on their pooled patient data, lots of hospitals, and privacy laws prevent them from actually pooling the patient data. So they want to somehow train the deep net without revealing the data. Or say you want to customize Gboard, the Google keyboard, for user groups, and the user groups have their own chats, private chats, and you want to customize Gboard on that without revealing the chats to Google. Universities may want to customize the Slack forums using private conversations, etc. And of course, you may want to hold on to your data instead of giving it to Alexa and Google and so on, and Amazon, etc. Okay. So there's a lot of prior research, and federated learning is a conceptual framework to think about it. For example, imagine that hospitals wish to train this deep net collectively using the data. And in federated learning, the deep net is trained at a central server. Hospitals hold on to their data and actively participate in the training. Everybody maintains a copy of the deep net as it's being trained. And using their local data and backpropagation, they compute gradient of the loss and send only the gradient updates to the server. The server aggregates updates from all the hospitals, aggregates the gradients from all hospitals, and sends back the new parameters of the net. And the training involves this back and forth between the hospitals and the server. So it's just a framework for thinking about distributed deep learning. Now, it turns out, even though the hospitals may appear to be holding on to their data in this framework, information leakage is occurring from the gradients that they are transmitting about using their data. It was shown by Zhu et al. Last year that any eavesdropper on the protocol can use an efficient gradient matching attack to reconstruct the hospital's data from their gradients. So in other words, we need some explicit method in this picture to protect the data. There are two standard solutions existing before. The first is differential privacy, which adds carefully chosen noise to the gradients. But its shortcomings are that the accuracy of the trained net plummets by a lot, 20% on CFAR10, and the accuracy drop is actually catastrophic on ImageNet, more complicated data sets. The second shortcoming is that it gives a very restricted notion of privacy. It's concerned with privacy loss due to the release of the trained model, that is proper use. And the reason has to do with the fact that differential privacy was invented in a different setting, namely privacy of databases. So differential privacy gives no guarantees about side computations using the shared gradients, which is what's going on in this gradient matching attack. So the second solution that has existed for several decades is cryptographic. Just as cryptography can protect our online transactions, it can also protect every arithmetic operation in any computation, including the computations done in deep learning. But the shortcoming is that it does this encryption operation by operation, and deep learning just has billions or trillions of operations, and it's not very efficient, although there's been some progress in making it somewhat more efficient. But also the other shortcoming is that it needs finite field arithmetic, which doesn't work very well with the real value arithmetic in deep learning and requires special setups such as public key infrastructure. So it's currently not a very practical solution. So now we come to the new idea, InstaHide. It gives a way to encrypt images. So you take normal training images and test images, and you can encrypt them. Now you can input it into the same frameworks that you have, the same code, PyTorch, whatever, Keras, and it can be used in the same training, same little blue guy. And you train and test on encrypted images. And doing this training on these encrypted images has very minor effect on final accuracy, as we'll see, and very little effect on efficiency, unlike cryptography. So it's better than differential privacy in that it has minor effect on accuracy, and much better than cryptography or existing cryptography because there is almost no effect on efficiency. And we think it reveals nothing about data, but it's a new form of encryption And violating privacy here requires solving some computationally difficult problem. This is analogous to existing cryptography, but it's a new form of encryption. Okay, so I'll give you some idea of what's inside this new encryption. It's inspired by a technique called mix-up. This is a form of data augmentation introduced by Zhang et al. A couple of years ago. And we theorists have been trying to understand what's going on with mix-up because it's very counterintuitive. Let me describe what it does. Mix-up, well, the training is on images, but mix-up interprets them as vectors. And the labels can also be treated as vectors. Now, with vectors, you can take linear combinations, and that's called mix-up. So you take 0.6 times first image and 0.4 times another training image, and you get this composite image, pixel-wise addition. So you get this composite image. And mix-up involves training on these composite images. Now, the labels themselves are vectors. So this is standard in deep learning that the label is a one-hot vector. It has zeros everywhere except one in the location corresponding to the label. In the first case, bird. In the second case, airplane. So the label of the mixed-up image is 0.6 bird and 0.4 airplane. So you train on these mixed-up images with these mixed-up labels. And surprisingly enough, this improves training. The deep net is never trained on normal images. It's only trained on the mixed-up images, and this improves training. And in theory, we've been trying to understand this because it's kind of bizarre that the nets which are so nonlinear are being trained to behave linearly. Anyway, I won't say much more about why mix-up works, but we're just going to use it at InstaHide. So one idea is that we'll do mix-up, but that's turns out is not enough, as we show in the paper, to ensure any kind of privacy. So what you also do is you mix it up with images from a big public data set, like ImageNet or Instagram images or whatever. And those also, so there are these coefficients, 0.6, 0.4, et cetera. These are chosen from some simple distribution. And you mix it all up. So in this case, 4 images. You get the composite image. And then on that composite image, you flip the pixel signs randomly. So pixels are, in this case, scaled so that they are, say, between -1 and 1. And you flip the sign randomly. And you get something like this. Remember that pixels are colored. And so when you flip the sign, you really change the color a lot. So you basically get this grayish looking thing. And that's the encryption. Why the large public data set? Well, because it's off the shelf, no special setup assumptions. You can just take any images out there. And large because this gives more security. This is formally, it's because the encryption key is the choice of images. And there are lots of choices for this in the public data set. And that gives more security. So formally, the general InstaHide strategy is that you're going to take mix-up of 2 private training images as you do in mix-up, and then k-2, k is some parameter like 6 or 4 or 8, and k-2 public images from this public data set, followed by pixel-wise random sign flip. And you're going to train on these mixed-up images, which look like blobs. So that's it. And you also do the same thing at inference time and do the inference that way. And the conjecture underlying the security of this is that this is based upon intuition from the classic subset sum problem, that extracting significant information about private images from the encryption, this blob, takes n to the k-2 time, where n is the size of the public data set. So since n is pretty large in, say, millions or billions, this is fairly secure, we think. And we put out a challenge data set, which you can try to attack. So here you can see that InstaHide has fairly minor impact on accuracy. MNIST, CFAR10, CFAR100, and ImageNet are standard image data sets. And you see that compared to vanilla training, InstaHide doesn't have a very dramatic effect on accuracy compared to, say, differential privacy. And the running time is not too different from vanilla training. So this is just the first cut. Maybe it can be improved. Robustness to attacks. This scheme has been out for a few months, and people have suggested various attacks. We came up with some attacks. We've run them. We can't seem to break them. But there, as I mentioned, there's a challenge data set out there, which you can try your hands on. Now I'll talk briefly about text data sets and how to apply similar ideas to text. So there are several complications. Number one, as you all know, images can be thought of as real valued vectors, but text is a sequence of discrete symbols. The second big difference, which is why it took some thinking, and it's a separate paper to do it for text, is that the current paradigm for machine learning on text is by fine-tuning one of these language models that I mentioned earlier. So you take this language model like BERT, which is pre-trained on a large corpus, and now to make it do some classification task, you take the embeddings produced by this language model, and you're going to input it into the classifier net. And you're going to train this classifier net using the label data and this text embedding. And so now gradients are flowing back and forth and training is going on. But there's two types of training going on. The classifier net is being trained from scratch. And the top net, the language model, is being fine-tuned. So where do you stick the encryption in this picture? You stick it in between the language model and the classifier net. Okay, so just in picture, going back to the hospital picture. So the BERT, or the language model, is sitting with the hospitals, and they have the secret text. And the classifier net is at the central server. And the hospitals are going to send over the text embedding. And the classifier net is going to send back the gradients. And the insta-hide kind of ideas are going to be used, what we call text hide, to encrypt these text embeddings and the gradients that are being sent. Okay, it's similar to insta-hide, but the analysis of security is completely different because it's being stuck in a different place in this pipeline. And it also has minor impact on accuracy on the standard benchmarks, as you can see on this. So I'll conclude here. We've introduced these methods, insta-hide and text hide, which are substantive advances on important technological and societal problem, how to allow deep learning on my data without revealing my data, and their potential applications to medicine, Alexa, Gboard, Internet of Things, self-driving cars, etc. You could easily imagine a sort of new kind of company built around privacy, which provides this kind of service and acts as an in-between between us and, say, Google and Amazon. All these methods are a direct plugin with a few lines of code to existing frameworks on existing softwares like PyTorch and Keras and so on, with minor effect on accuracy and on efficiency. And the power of these ideas may cast new light on other open problems in security, privacy, and robustness. Hopefully this fresh take will stimulate other works. Thank you very much. And I'm looking forward to more theoretical understanding of deep learning.
Thank you very much, Sanjeev. That was a wonderful talk. Let me now welcome Yejin Choi, an associate professor at the University of Washington and a senior research manager at the Allen Institute for Artificial Intelligence. Yejin, please unmute yourself and start on your presentation.
All right. Thanks, everyone, for having me here and joining the talk today. So I'm excited to share our recent adventure in cracking commonsense intelligence. So why commonsense intelligence when today's deep neural networks seem to solve everything, starting from object recognition, machine translation, and so forth? Looks as if we've done solving AI and we can all go home, or not. So the state-of-the-art models are not very robust when presented with adversarial examples or out-of-domain distribution, not only for computer vision applications, but for NLP tasks as well. So it looks as if right now we know how to solve a data set without really solving the underlying task. So why is that the case? Well, there's a fundamental difference between how humans understand the world and how machines mimic that understanding only through pattern matching in data sets. So how do we bridge this gap? It's good to think about how human cognition really work and then see what sort of major things we are missing out of that. So for that discussion, this system 1, system 2, reasoning comparisons became quite popular thanks to Thinking Fast and Slow due to Daniel Kahneman, the Nobel Prize winner. But the downside of it is that it seems there's a major misunderstanding going on in the field that perhaps we figured out how to do system 1 reasoning with deep learning and we only need to figure out how to do system 2 reasoning. I dare say that that's a major misunderstanding. So Kahneman's earlier work actually talked about 3 cognitive systems: perception in addition to system 1, system 2. And perception and intuition together are the sort of processes that are fast, associative, and automatic, whereas system 2 is the one that's slow and effortful. And then what's really interesting is that both the system 1 and system 2 require conceptual representations and require reasoning about past, present, and future. And both are important with respect to language. We cannot really do things that far without language. So we can think about what sort of applications correspond to these different cognitive systems. So for reasoning 2, system 2, we often think about solving puzzles, writing programs, or solving logic theorems, but also reviewing or writing scientific papers will require system 2 reasoning as well. Well, hopefully, reviewers do involve system 2 reasoning when reviewing our papers. So what we seem to be doing really well right now seems to be more belonging to this perception level system, like object recognition, image segmentation, and speech recognition, and so forth. In between lies this something really quite interesting, which is all about intuitive inferences, reasoning about preconditions, post-conditions, what happens before and after, people's motivations, intents, and their mental states. We do this almost subconsciously every waking minute. So this is going to be the focus of my talk. And to make my point a little bit clearer, let me show you this Roger Shepard's monsters in a tunnel. What do you see here? It's not just 2 monsters in a tunnel that you see. You see stories, like 2 monsters are running as opposed to standing still on 1 foot. And one is chasing another as opposed to copying his body movement, or the chaser is hostile and the chaser is afraid, even though 2 faces are actually identical. We almost hallucinate all these stories, explanations, and imagination about what's going on in that particular image. So 2 important observations here. A, none of these inferences have to be absolutely true. The inferences are stochastic in nature. Everything is divisible with additional context. More importantly, a lot of these intuitive inferences are sort of common sense inferences, and a great deal of that can be best described in natural language. And when you do that, we cannot just do it with just words or graphs of words, but we need the full scope of natural language. I already showed you 3 examples here that are in natural language, but let's look at another example. So this is a snapshot from the movie Titanic. And so what do you see here? Well, if we ask computer vision state-of-the-art systems, you might get some set of objects that are correctly identified. But when you look at this set of objects, you don't really see what's going on. It doesn't really capture the gist of what's going on in this image. So then we might think, well, let's add more interesting words and then even create some relations between the 2. And certainly we are heading to more informative direction, but still, when you look at this graph, do you really see what was in the original image? So that's where the necessity for full sentence description comes in. But if we just do state-of-the-art image captioning again, it doesn't really explain why this person is doing what he's doing. Is he having fun and trying to sail a statue in the water, or try to save himself from drowning? In addition, we almost see dynamic context of this image. For example, what might have happened seconds ago, or what might eventually happen down the road. So in order to address this sort of reasoning about the dynamic context of a still image, we presented the visual comet at ECCV this year. And the gist of it is that given an image, we want to be able to predict everything, all these octopus tentacles at once. And this is really the nature of human common sense inference. So we annotated this for not only 1 image, but for many others. And what it culminates is this connected graphs where you can see nose like screaming for help, and then see in what sort of visual situations you might imagine to hear that auditorial sound that you cannot actually hear from those still images. And then crashing the car. So this is what might look after crashing the car, and this is the moment perhaps before crashing a car. Without really looking at that particular moment of crashing the car, we can still reason about before and after. So we have this new resource, which includes 1.4 million common sense inferences described in natural language over 60,000 complex visual scenes. Whenever we have this sort of data, we can now throw in our favorite neural network architecture. Not going to go into any of this detail. Let me just highlight one particular qualitative example what this sort of a resource might enable. So here, person one is putting up a letter on the table at an outdoor restaurant. So this person one, if you look closely, is a serving person. And what's his intent? Well, he wants to serve other people, have them eat. And then afterwards, he probably will get back to the kitchen to get more food. So by having this sort of resource, we can train neural network to mimic the sort of intuitive reasoning or common sense reasoning that we do. And in doing so, it's really important to realize that we need the full scope of language, not just words or graphs of words. And if you buy that, now interesting corollary to that is that reasoning becomes generative task as opposed to discriminative task. What I mean by that is that, you could insist that I'm going to consider 1 million possible sentence descriptions of common sense inferences and then try to take it as a discriminative task, evaluate all 1 million choices and then rank which one comes the best. But that's certainly how we speak and reason in real life. We tend to almost generate token by token, word by word in real time. And I think this is really interesting aspects of the efficient reasoning capability that humans have that we need to investigate more in current AI. So we have prior precursor works to visual comet, so Atomic and Comet, that I'm going to briefly describe. So Atomic was presented that last year. It's an atlas of machine common sense for if-then reasoning. And so this is all about text, and it concentrates a little bit more on social common sense. So given a center event like X repels Y's attack in the middle, what we can infer is like causes or preconditions of that event. So perhaps she wanted to protect either other people or herself. And we don't know which is true for sure, but these are reasonable predictions about her intent compared to, she wanted to sleep. That's completely unreasonable. We can also reason about effects or post conditions, such as a result, she might feel angry, she might want to file a police report, her heart might race, he might fall back, and then either he might want to run away or attack back. So there are different types of reasoning we can do for the dynamic state changes of the world. Now, some of these inferences can be about static attributes, like a personality being skilled, brave, and strong, that do not change minute by minute. So this is more static in nature. So we had a lot of this. And in order to build this graph, you might wonder, can we just extract this knowledge from a lot of web data, because there's a ton of that. The problem with that is that there's a reporting bias. So people do not say obvious things, and AI might just think that, well, humans murder each other 4 times more often than we exhale, because we don't really say how often we do exhale. And so it's not going to be accurate enough. We decided to fully crowdsource the knowledge graph in order to see what happens. Before I tell you that, though, super brief remarks on how this differs from what you might have heard about. So for example, there's a psych, something called the psych, and then there may be other favorite resources that you're aware of. So there are 2 fundamental key differences that I want to emphasize. A lot of the prior resources focused on knowledge of what, or taxonomic knowledge, that penguin is a bird, but that's really not enough. We need knowledge of how, knowledge of why, which corresponds to more of an inferential knowledge. We do a lot of reasoning almost by memorized pattern matching, even as a human, and why not? AI shouldn't do that. So another major difference is this logical form. So not all, but a lot of prior resources were in this form. And when you look at this, even as a scientist, does this make immediate sense that it aligns with your common sense understanding about how the world works? It certainly does not speak to me right away. And so in our resources, we are going fully natural language. And this really aligns with what Sanjeev said earlier about how natural language modeling can be very beneficial for downstream applications. And as it turns out, that's exactly the case with the common sense modeling as well. In any case, we focus on causes and effects in order to better address this concern against deep learning, even though we still like deep learning. So speaking of deep learning, here comes common sense transformers, which starts with this question. So Atomic had 900,000 if-then rules, common sense rules or rule of thumbs about how the world works. Is this really large enough? Or is it just in a tiny little corner in this universe of knowledge that you and I share? I speculate that the answer is likely to be the latter. So then what do we do? Do we try to somehow extract more knowledge and store all of them explicitly? And my speculation is that we don't need to. So it's better to build a model that could generalize for knowledge that's not even stored. For example, if I ask you whether butterflies are bigger than elephants are bigger than butterflies, you don't have to store the knowledge a priori. You can just think about butterflies and elephants and then answer it on the fly. So that's what we want to do. In doing so, we are going to benefit from transfer learning from language to knowledge by starting with pre-trained language models and then continue train that your favorite transformers on our atomic knowledge graph after serializing atomic knowledge graph into a long string of text. So now this transformer keeps reading common sense descriptions, and then here's an online demo you can play with. But it turns out this comet generalized much better to out-of-domain examples than we realized at the time of publication. So here's some fun examples. Sanya rides into the sunset on a motorcycle after solving AI. Atomic doesn't have anything about solving AI. Also, Atomic doesn't have these people's name, Sanya. It's all about person X and person Y. But Comet doesn't mind, and it predicts seemingly reasonable predictions like maybe she was having fun, and then she might be seen as someone daring, brave, adventurous, and so forth. How about Gary breaks the world record for most controversial tweet? So Atomic doesn't know anything about tweet or controversial tweet. Doesn't know which Gary we're talking about, but it produces fairly reasonable inferences, like maybe he wanted to be famous, maybe he wrote a book, wrote a blog post, and might be seen as very famous and influential. Maybe he feels very accomplished afterwards, celebrate, tell everyone about it. So Gary Marcus, as we know, has some concerns about deep learning. So this is one of my favorite tweet messages that he wrote about how GPT-2 is not up to his expectation. So he gave this prompt. What happens when you stack kindling and logs in a fireplace and then drop some matches is that you typically start A, and then GPT-2 goes on to say some nonsense. But that's because GPT-2 is really language model. So try Comet, which is knowledge model. And it turns out it just works right away. So Gary wanted to start the fire, which is pretty good. So let me now share closing remarks and open research questions. So if you search common sense, the word common sense from ACL anthologies, so this is a repository of all the NLP papers. Most of them are either from 80s or from the past few years. So there's this curious void, significant void in between. And indeed, when I was thinking about studying common sense several years ago, many people in the field advised me, don't do it. If I want to be taken seriously, don't do it. Don't even speak the word, as a matter of fact. But the more I think about it, the past failures are inconclusive when they were based on weak computing power, not much data, no crowdsourcing, not strong computational models, like no transformers available. And then their conceptualization and representation choices were not quite right. It was too much of logic focused. Whenever you play with the logical forms, there's a serious loss of information. So language is the way to go. Fast forward, it seems that the new generation doesn't know these past failures, so they're much more optimistic. So we held this first common sense tutorial at ACL this year, which to our big surprise was second most popular. So it seems that there are a lot of interest for common sense, or growing interest for common sense. But what is the path forward, really? This is sort of like almost a moonshot research goal. And well, I personally don't know how to get there quite precisely just yet. But one thing for sure is that brute force larger networks with the deeper layers will not do it. By analogy, you don't reach to the moon by making the tallest building in the world 1 inch taller at a time. So let's just step back and really think about the current paradigm of how neural network solves leaderboards. So oftentimes it's you give this lots of exam problems and then let it learn. But the problem, there's a really big problem with that, multiple big problems with that. One is that the neural network inevitably lets on spurious biases in the data set and pretends that it knows how to solve it without actually learning the fundamental concepts correctly. But let's really ask this question. Are we even able to do this? Like imagine taking a deep learning class, professor doesn't teach anything, but just to provide you with a lot of multiple choice questions with the correct answers, and you're supposed to figure everything out on your own. I don't think even a human can do that. Alternatively, let's just say, the professor just provides a lot of deep learning code so that it's a little bit more like self-supervised learning now. I don't think humans can really learn efficiently that way either. So we like taking classes, reading textbooks, learning from tutorials very, very early on in our education. And I think we really need to think about how to teach machines, AI, with a declarative knowledge in a similar manner. The other question to think more about is this evaluation paradigm. Multiple choice is very attractive because it's easy to evaluate. But what you cannot, as Richard Feynman said, what I cannot create, I do not understand. And one way to interpret that is that, well, unless you can generate the answer, you cannot really prove that you really truly understand. And it's also like assuming that some oracle always provide us with like 4 magical choices to choose from, of which one of them is guaranteed to be true. That's just practically not very useful assumption to make. So I'm beginning to think more and more that we need somehow a way to teach machines some concepts in a more direct way. And what I just presented in this talk is one way to get there. It's not the most perfect way of getting there, but Atomic is basically a textbook of common sense knowledge in declarative form, which contrasts with the observed knowledge that's implicit in lots of raw text that language models are trained on. And in doing so, we use language as the symbolic representation of knowledge instead of logic, because logic can state just so much. A lot of examples that I was using today are deliberately chosen to demonstrate how hard it would be to translate all of them down to some consistent logical forms. We need to focus more on causal knowledge. And then neural networks are really great for generalization to compositional and previously unseen events. I've kind of felt like Atomic and Comet together are so 2019 though. So we have this 2020 version coming up, which I'm not going to go much into details other than to say that, well, it just has a lot more new relations, even including how money might be used not only for paying repairs, but also folding origami, which is kind of cute, or what sort of events can be hindered by. So you cannot get your car repaired if the cost is too much, or the car is totaled so that it's just not amenable to repairment. So keep going on this so that we have plenty more. But skipping over all this, let me just highlight one thing about these likely questions that people have in mind. Doesn't GPT-3 by any chance solve all this on its own? So let me give you a little bit of context to consider though. So our model Comet, now it's based on BART, is much smaller than GPT-3. So it's about 400 times smaller. And GPT-3 is so big so that it's not easy to download it and fine tune it to customize it for your own downstream anything. So with that in mind, GPT-3 is doing really great considering how it's unsupervised off the shelf with a few shot examples, but still A, there's a considerable gap. B, it's too large, and whenever you can use a smaller one, why not? But this is for some of the simpler common sense knowledge that we evaluated on. But what about morality? Because we do worry about AI safety. So I gave this prompts last night. Running a blender at 5 a.m. is rude because you can wake up the entire neighborhood. You can only do it if you're making a thick smoothie and need to incorporate some ice. Wow, that sounds nice. I can do that if I do it. So it's a little bit confused, but not so bad. But how about it is okay to post the fake news if, and then GPT-3 says it's in the interest of the people. So I was thinking, I don't know about that. And then I tried once more, and then it says, ooh, it's even worse. So don't say that to me. So here, the takeaway message, by the way, we have a new paper, Social Chemistry 101 for reasoning about social and moral norms to appear at EMNLP soon. And the paper might be on archive or will be archived within 24 hours or so. But basically, the idea is that we need to teach AI with descriptive ethics in the form of declarative knowledge. It's extremely unlikely that brute force large networks with some fancy schmancy self-supervised learning will be able to discover all this magically. Another really important point is that social moral norms cannot be really done without the full scope language incorporation. Compared to descriptive ethics, there's another more prescriptive direction where you might just focus on a few central dimensions of morality and then focus only on that. But if you do it that way, you cannot really translate that to natural language descriptions of a particular situation, like the way that I showed you here today. So we really do need to embrace language, which was sort of the recurring theme in this talk. Let me add just one more thing on top of this generative reasoning angle. It's not just me. It turns out that there are cognitive scientists who are talking about similar things. So The Enigma of Reason is one of my favorite books that I discovered the past year. And in it, it talks about how intuitive inferences are a great deal about extracting new information from the information already available, like a common sense inferences. But here, so reasoning, system 2 reasoning are used primarily not to guide oneself. Here, guide means making an important decision, but it's used in order to justify my decision in the eyes of other people or convince other people. So here, the position of these authors is that really reasoning serves the purpose of a communication. Language is really deeply involved in system 2 reasoning. And it's similar to how I might have made this intuitive decision already that I'm going to work on common sense, but how do I now justify my decision? Well, now I need to really involve system 2 reasoning. And in doing so, human reasoning is a mechanism of, or system 2 reasoning builds on top of intuitive inferences. It's not a separate thing. They're really integrated with each other. And conventional mathematical logic plays at best a marginal role, which also repeats in this Philip Johnson Large book on how we reason. Okay, so I'll stop here. I'm exactly at time. Thank you.
Okay, thank you very much, Yejin, for that thought-provoking talk. We'll see you soon for more discussion in the panel session. Our next speaker is Aude Oliva, MIT director at the MIT-IBM Watson AI Lab and co-director of the MIT Quest for Intelligence. Aude, you may now unmute yourself and share your presentation. Thank you.
Good afternoon, or good morning, everyone. Thank you very much for giving me the opportunity to speak today and attend the panel later. So while I was putting together this talk on incorporating insight from cognitive science into AI, I realized that since my freshman year at the university, which was over 3 decades ago, I have always combined knowledge from different disciplines. At the time, there was mathematics and philosophy, but particularly cognitive science, neuroscience, algorithm. And it started being difficult for me to separate those domains, where an idea comes from, as I really tend to think of a task or a solution really melting all those domains. And how to become a bi- or trilingual in different domains of science and technology is a training that I try to bring to my students So I think it can give a richer and different view on the question of intelligence. So today I will present a few examples of the work we are doing in my lab at MIT, trying to use good ideas coming from cognitive science into AI model. So first I will describe some very concrete example of how we can leverage cognition for machine learning model. I will only speak about 2 or 3, but if you open a textbook in cognition or neuroscience, you will find hundreds of useful concepts. I still am one day to write a sort of integrative human AI cognition textbook, we'll see. And I will also share some neuroscience visualization about the human brain, which shows how the human brain is at work during seeing and hearing, which I think could really inspire the next generation of cognitive architecture. So one of the main projects we have been developing in my lab at the core of cognitive AI is how do we build a system that can recognize the visual world? And you can see here a few of the milestones from scene and activity recognition to common sense reasoning that actually are all inspired by a cognitive concept. I believe this milestone are needed step to bring cognitive capabilities of the model to the next stage and have the model being an interface that people can understand and relate to and communicate with. So which kind of cognitive concept did we concretely use in our study? So events in the world, just looking around, they unfold in time and they unfold at different temporal scale. So the question we ask is, well, if we want a model that is able to understand and recognize what's going on, what is a meaningful moment? A meaningful event that the model could learn and capitalize on? How long is a meaningful event? And then how long should the video be to train models that are going to be able to recognize what's going on? So we created the Moment in Time project at MIT that is led by Matthew Munford, which is a large-scale data set with 1 million snippet video of 3 seconds and over 2 million label currently. And this whole project started 3-4 years ago with a simple observation. 3 seconds. This is just enough time to size up a scene, to size up what's going on in an event. And 3 seconds is the short-term temporal window that holds meaningful action between people, object, phenomenon, things happening in the world. It's also a window of time evolved as humans face the physical and corporal constraint. It takes time to move, pick up an object, and so on. And in the experiment we did across neural network, 3 seconds seems to be enough to learn very robust video representation in order to transfer the representation learned in a model to of a task. So if you take a long random video and you cut at a long video and you cut at random segment of 3 seconds, you will have a very high probability that in that segment there is a meaningful event, and you show to people and people will say, oh yeah, this is what's going on. So in the Moment data set, all the cuts were actually originally selected at random, and then we labeled them in crowdsourcing experiments, which gave a lot of diversity to the data set. So if an action of an event is more than 3 seconds, well, 3 seconds is kind of enough to have the gist of it, so to train the model. And if an event is less than 3 seconds, then it's good because you have the event in context and you know a little bit what's come before and after, which is going to be important for building model that will rely on causality at some point. So here are some example of what our model that we are trained on those 3 second snippet for activity recognition are able to do when they are faced with new new video, and here's like the raw output of the model. In red are the zone of attention where our activity recognition model focus more in order to tell you what's going on and give you some of the words that you can see at the top left of the screen. So let's keep running this, boating, skiing. So you can access the work on our website or papers as well as download the data set. So this was a very encouraging project, because if you have a backbone basic event recognition model that can give high accuracy and coarsely localize what's going on, it means that, well, there's this basic recognition of the activity that is checked. And our idea was, well, when this ability is developed, what can we do with it? What can we build on? And we actually build models that can perform abstraction by linking events that look very different, like the one you saw here, the event of cutting the tree or separating the papers. They both belong to the class abstraction. And what I'm going to show you, we were able to reach that level of abstraction in our model because we had a very strong backbone. So I do think that when you think towards going to a high level goal, a cognitive AI system, it certainly worked for us and our team to think into milestone and see when we achieve a milestone, how it can be used for the next step. So I speak about abstraction, but what does it mean, abstraction, for an AI model? So let's play a game. So here is an example of a game, and we had our model and people playing the same game. Which action best match the reference set? So if you look at the top row, there are 3 videos of persons sleeping and resting or doing some yoga. And the game is, you're giving another set of video and you have to choose which video best match the original set, here represented under the blue. And when we gave this to people, most of people selected, as you may see watching this, the little cute dog sleeping. So now the example on the bottom left. So we have going upstairs or also climbing. So that is the match set. Game is given a set of other video here too, which one those fit the best. The same concept, abstract concept of the top one. And when we run this, most people selected the chimpanzee clinging. So now look on the right at those additional examples. So the match set here shows some, there's some actually water that is falling down, and the other one is as well a cartoon also falling down. And so which one of the 2 video in the bottom does match the reference set? And if you look closely, it's actually, well, it's a tricky question, but most of people we gave the task to responded this one. So not a trivial task, but a game that now model and people can play. So let's now have another game, which is very related. So now you have a set of video, 3, 4, 5. So let me play them. This one, this one, this one. And the game is which video or event does not fit the 2 other. So which one is the other one? So think a moment, look at those. And in our task, most people have selected this one as being the outlier. So let's see another example. So all with water. Again, same task. Which event could be the odd one? Actually also a difficult one. Well, given this task, the higher responses that we got from people was to select this one as the odd one. So in all the example I've shown you here, we had people and our new model of abstraction playing the same game. And they choose the same image most of the time, about 75% of the cases. So what did we do to make the model playing pretty well at those two games? Well, we taught the model the notion of abstraction, that we execute, operationalize here as what is the common concept that connect a set of video, a set of 2, 3, or 4 video. So here is an example. What those 3 videos have in common? Take a moment. What can connect them at a higher concept, an abstraction level, a description of the activity? So people will easily understand that those actually depict the same some sort of competing. Current machine learning model struggle at inferring this abstract connection. Although we are seeing very fast progress almost every week or month. There's some nice breakthrough out there. So in the framework that we propose, this is a project that is led by Alex Andonian and Camillo Fosco at MIT that was just presented at ECCV in August. Our abstraction framework combined the visual features with natural language supervision to generate a richer representation of the action video have in common. And think about how you teach young kids about animals or things going on or concept. You actually speak to him or her all the time. So it does make sense that in order to build up representation that are going more further away, the exact depiction of the object and the scene and the things into a video, you speak to the person. You had that language representation. And this is what we did in this work. So for instance, the model has learned that exercising can take many forms: running, lifting, and boxing. And its feature representation mixed with language can be used then to play those games or those 2 new tasks, which is find the event that fits, so set completion, or find the one that doesn't fit. So what I'm showing here is actually still a toy model. We actually produced 2 models, one based on moment in time data set and one based on kinetics for generalization. And so there are multiple dimensions that you could imagine people focusing on when they have to play those games to find what fits or doesn't fit. In this particular paper, we focus on activity, and we also told people when they were playing the game to focus really on the activity. So here actually very interesting sort of the other output is basically what was the type of information that the model of abstraction were using when it was taking the decision. So here are a few examples of just the raw abstraction output of the model, when we can also ask the model, well, if we give you those 2 videos or those 3 or 4 videos, what is the abstraction that is common to those? And here it shows some of the responses of the model, and some are they make a lot of sense, and some are really interesting, how you could make link with things that we might have not make links to. And the output also give you the sort of focus of attention, which is where the model can focus to produce a response regarding the type of activity. And what I think is very interesting in model that can take decision at this more abstraction level, and we start seeing quite a bit in the literature, is that it's a framework in order to perform few short learning or even 0 short learning, which is generalizing to new classes with few or no example, as well as getting a little closer to human-like abstraction abilities, which has been a new experience into conceptual categories. So I just gave you example of a couple of projects and two cognitive principles. There are 100 out there, and it will be a really fabulous journey if all the cognitive, the computer scientists out there were starting reading the textbook in neuroscience and cognition, because there's a lot of gold literally hidden in every page. And there is more gold that you can find when you start working on the neuroscience of the human brain. So let's now look at what we could learn from the human brain that could start inspiring tomorrow's model that are more complex, which are architecture of cognition, because they could start taking into account a lot of the perception and thoughts that we do when we recognize or when we move in the world and so on. So one of the most important aspects of the brain, besides being a deep learning network, it's a dynamic deep learning network. The information that comes to us in the world and it's processed into the brain is processed in time. So temporal sequences, things that happen or that are processed in parallel or one after the other, is a very important element of human intelligence. And we do not know very well how to deal with timing and the right sequence of processing an artificial neural network in order to reach some more cognitive level AI and tasks that unfold in time. And if we want to understand human intelligence and see how human and artificial systems could interact better, I believe we need to really have a good understanding of how things unfold in perception and cognition in the human brain. So capturing the temporal sequence of brain perception is not easy. There's a few methods out there, but this is another line of research in my group at MIT. And in 1 or 2 decades, this slide will really look like the cavern age of cognitive neuroscience. But these are the tools available to a lot of the neuroscientists today. So in our experiment, we have people doing the same exact task and experiment twice in 2 machines. One in MEG, and then they go in fMRI or the other way around. So MEG, or magnetoencephalography, is a functional neuroimaging technique for mapping brain activity by recording magnetic fields produced by the electrical currents that naturally occur in the brain when you look or hear at things. And it's using very sensitive magnetometers. fMRI, or functional magnetic resonance imaging, measure the brain activity by detecting the changing associated with blood flow. And these techniques relies on the fact that the cerebral blood flow and neuronal activation are related. So when an area of the brain is in use, the blood flow to that region also increases. So in this line of work initiated with Radosław Ciszy, we combine the data from those 2 very different sensors using different machine learning techniques. And now let me show you an example of the brain responses to images shown for only half a second. So here is what half a second feels like. You see a lot, but it's kind of fast. All right, so here is our brain model, and you can see a timer. So when I start the movie, it's going to go fast. At some point, you're going to see some of the region lining up with different colors. And this is what we recorded. We put here together about 15 people, 15 brains to show you this. When we were showing a series of images for half a second each, as you saw in the little demo. All right, so we have this started, and we can start seeing some responses that start coming around, you see 70 milliseconds over here. And they start in the back of the brain. That's normal. We are showing images. There's no sound in the scanner. And it shows that, well, it's perfectly expected. Information goes into the occipital, and we start seeing some responses. So that sort of study that was published initially in 2014, actually we did replicate a lot of the work, and since more have been replicated, recording things we absolutely know about visual processing. Oops. Which is that as we see and time unfold, information is envisioned and then it flows on both sides and on the temporal side of the brain, and then so on and so on. So I show you here a large visualization. But what the neuroscientists do is that they go and dig into the responses of every single brain region. It's like it's a map. We have a lot of modules, and we have a good idea of what each brain module does. So the one we will see, the one we will be used for imagination, and so on. It's really a journey to dive into the result, but it's a way to track down what's going on, and it could really inspire new architecture when we show all the type of activities. So in a similar vein, we also run those neuroscience experiment with sound, and we put people into the two scanner, and we had them listening to snippet of sound for half a second. So sound were represented voices, animal sound, objects like the telephone, toys, cars, and environmental sounds like wave, storm, and so on. So now let me show you what we observe. There's a lot to see here, and there's a few really nice new nuggets of information. So now it's sound. So the here are here. So normally all nice expected is start on the left and the right in the temporal lobe. So this means here that the information regarding the sound has been perceived. And then many other brain regions are going to start responding. And I'm going to stop here. And you see on the Y representation of the brain, you have in the front this region, this sort of isolated region. And this is actually a region that is more specific to process voices and animal sound. So when we go through those results, we see that within 150 milliseconds, there are many areas that are processing sound, and then the area processing sound start really spreading to the area that are more visual area processing sound. So what this sort of visualization show you is that actually processing sound from the brain, when you compare to vision, is much more complex. There's a lot of regions that are being engaged either in a sequential or parallel manner, and we really are in the process of segmenting all this in order to have some more clear guidelines about how sounds are processed in the human brain for some future architecture of cognition. And I show you here vision and audition, but you can play the same game with tactile information or memory and so on. So I've shown you example of this incredible engine that's the human brain when it processes sensory input. But it's also important to characterize the bandwidth and the boundaries of human perception and cognition. Let me show you what I mean. So let's say you're in the street, you're just waiting a few seconds to cross the scene. You're not looking particularly anywhere. Maybe you're even lost in your thoughts. Oh, well, did you notice anything? Let me show you. So here is basically what happened in front of your eyes. All those elements were changed literally in front of your eyes. And cognitive science has developed methods to quantify what we can see and not see, here and not here, to characterize our perceptual bandwidth, the boundaries and how flexible it is. And I think that many of those concepts of the cognitive bandwidth will be very informative to have systems that interact with people. Here is again the demo, if you just missed it. Yep, you did miss a lot. So to conclude, biological and artificial neural networks, they are like to me, the two faces of the same coin. Both biological and artificial can differ a lot in their architecture, their circuitry, their learning rules, their objective function or task, but they are both systems that use iterative optimization process to pursue an objective given a lot of data, and there are many common ground and principles between them. So I think that characterizing the bandwidth of human perception and cognition is very critical. And when you start digging into thinking about intelligent system, you're going to need to go and look at what's going on in those systems. And that may unravel a new field of investigation: cognitive, clinical, social, computational, experimental. It's the sort of synthetic neuroscientist that's going to really dig on and understand what's going on in the model. So as we see more interactive system, it's going to be important to study the implementation that works best for performing specific tasks, will help to explore the alternative that have not been taken by biological system. And most importantly, I think that in all the system we are building, at the heart of this endeavor, we need to integrate decision about ethics, social responsibility, and the risk of AI into our pipeline. Thank you.
Thank you very much, Aude, for that wide scope from neurons to large-scale activity recognition. Now I'd like to welcome the final speaker of the session. Josh Tenenbaum is professor of Josh Tenenbaum is professor of computational cognitive science at MIT. Josh, you're already up, I see. So please start your presentation.
Okay, great. Thanks. It's a great honor to be here to talk to you about scaling AI the human way. I should say that, like many of the other speakers here, I've been working on this triangle and the bidirectional interactions between the science and the engineering of AI for my entire career. It's what I got excited about originally. It's what got me into the field. I'm going to tell you about the work that we're doing here at MIT in the Brain and Cognitive Science Department, as well as CSAIL, and in the Center for Brains, Minds, and Machines, and the Quest for Intelligence under MIT. But part of why I feel like it's such a great honor to be here is I really got my start in this field as a visiting undergraduate at Stanford in the summer between my second and third years as an undergraduate, where I worked with Roger Shepard and David Rumelhart, two people who've both been mentioned here before. And that's really where I got my basic idea about how to think about the mind, why it was so exciting and interesting, the connections between mind and brain, and how computation can enable those connections. Like many of the other speakers here, my work is fundamentally motivated by asking, why do we have all these great AI technologies, but no real AI? So why do we have machines that do things we used to think only humans could do, but nothing that has the flexible general purpose intelligence that you use to do each and every one of these things for yourself? What's the gap? Right. And again, I think especially some of the discussions that came up in the early session and some of the things that Yejin was saying, especially to resonate with this. I think part of the gap is that, we've made a lot of progress in AI technologies using techniques from machine learning, deep learning, and reinforcement learning that originally came from, just as Matt gave a beautiful history, right, from the psychology basically of animal learning. So studying very basic equations of like Pavlov's dogs, reinforcement learning in animals, or rats in a maze, right? So these, and I think we all agree that these can become powerful tools for finding associations and recognizing patterns when you scale them up in big data sets. But it's just one part of intelligence and maybe just one small step towards real understanding. So I'm interested in taking the next step, which comes more from a human-driven point of view, to say, well, in human intelligence, we don't just find patterns, but we build models. We are about understanding and explaining what we see. We are about imagining things that we could see maybe, but we haven't yet, maybe that nobody has. And then planning actions and solving problems that come up when you want to make those things real. And then learning as building new models of the world as we experience both our successes and our failures. So to reverse engineer this, to write down essentially the equations of model building, we're starting with young children because they're the original model builders. And again, like many of the other speakers, we're inspired by, could we build human-like AI that starts with just the basic kind of common sense that you see in these 1.5-year-old children? We're far from that. But imagine if we could do that, and imagine maybe longer term, if we could build intelligence that grows all the way into adult human intelligence, starting from the way babies start, right? This might not be the only route to human level AI, but many of us think it could be the best bet, because if you think about it, in our known universe, it's the only example we have of a system that reliably, robustly grows into human level intelligence starting from much less. And we know that even small steps towards this, could be big. So we're starting with the kind of most basic common sense that you can see in every 1.5-year-old, but no AI yet, like the intuitive physics that you see in this kid here, stacking up cups or playing with blocks. What is the knowledge that lets him, say, make a stack of 2 cups there and put it on top of a stack of 3 cups to make a stack of 5 cups? That is knowledge of objects, but also multi-object, multi-step plans. Or the intuitive psychology that you see here in the famous experiments of Felix Warneken and Michael Tomasello. The understanding that lets that 1.5-year-old kid in the back there literally read someone's mind, see this adult doing something that he's never seen before, but figure out what he's doing and why, and even how to help him. And you can see that here when the adult pauses and the kid does, well, exactly what you see him doing, right? It's an incredibly sweet and cute moment, and it's also remarkably intelligent. Just think, if we could build robots with this kind of common sense and helpfulness around the house, it would be amazing. Now, we're far from this, and I think in order to engineer this kind of abilities in AI and to understand in engineering terms what's going on in these kids' heads, we have to face some hard problems of common sense. And here, it's going to resonate again with especially some of the things you just saw from Yejin. But this is partly my way of introducing what I mean by common sense, okay? I also want to contrast our approach with the approach you saw, especially in the morning, from Matt, Dan, and Chelsea. I should say, I'm a big fan of all of them, and I'm grateful to have collaborated with all of them actually on papers, especially with Dan in some recent work that I'll mention here, okay? But I think, in each of their talks, you saw fundamentally a sort of bottom-up, learning-driven approach, which really takes as the core driver of intelligence the tools of deep learning and reinforcement learning, and add some other stuff to it maybe, okay? But I think these hard problems of common sense just show us what some of the limitations of a purely bottom-up learning approach might be. Some of the ways in which, though we're making great progress there, we might be more, climbing trees or ladders and so on, rather than getting to the moon. Okay? Not that those aren't really interesting trees and ladders, and not that these techniques are also, as I believe, part of the bigger picture. I think very much they are. But think about these problems of generalization. Like as Chelsea put it, like if we want strong generalization, right? We might want to build systems that get broad training data so that they can generalize just as broadly. But the problems of generalization aren't just the strong generalization, as Chelsea was calling it, or Sanjeev was talking about, where we have, like, say, distribution shift, but what I might call super strong generalization. So generalizing to environments that are vastly different from training, with essentially no retraining or fine-tuning. Or generalizing to an infinite range of novel tasks with essentially no retraining or fine-tuning or examples of somebody doing the same task, because maybe you just invented the task yourself. So just to illustrate one of these strong problems or super strong problems of generalization, think about this scene understanding task, understanding what's going on in a basketball game. So here's a typical image of a typical basketball game from the viewpoint that somebody who doesn't play basketball but might be watching from the side might see. Okay, and you see some images like this, or some scenes, and maybe some people tell you some things, and you understand what's going on. The objects, the balls, the players, the hoop, the goals, and so on. The teams, who's helping, who's trying to hinder or block others, okay? But whatever understanding you get about these events from this viewpoint generalizes to this viewpoint, which, until you saw a camera put at the rim of a basketball hoop like this, you never would have seen this activity here, but you have no problem generalizing to this, even though it's very far from the distribution. But this is actually still an easy problem of generalization, because think about all these other kinds of ways of rendering the scene, for example, in a video game. So here's a sports video game where it's fairly realistic graphics, but different at all sorts of low-level pixel statistics, as well as some not so low-level things like that circular hoop you see on the player being controlled, which is just something that comes up in a video game, but you have no trouble sort of factoring that out. Or take this video game here with less realistic graphics and much less realistic physics. You see somebody making a slam dunk going much higher than any human basketball player ever jumped, but you have in some sense the physics of all of your experience. Or think about kinds of things which again are much less different or much more different at the pixel level. And this again resonates to me with what Matt was talking about, where in some sense common sense isn't just about pixels. So take Minecraft, where you can see a basketball game, but the pixels are so different, and indeed even the objects are quite different in their composition, but it's the same thing going on. Or take this really old classic Atari game of one-on-one basketball. So different, right? And yet you have no trouble understanding it. Or lastly, the really classic Atari game. This is the Atari 2600 basketball, where it's ridiculous graphics by today's standard, and yet you still have no trouble, and kids can play it just as well. And the first time you see it, you understand exactly what's going on. Basketball hoops, players, ball, shooting. In some sense, these are all the same thing, the same activities, events, objects, agents, places. So I want to understand what is the common sense that allows me to perceive and make sense of this. Okay. Now, I think this poses a severe challenge to a data-driven learning approach. And this is a challenge that has been highlighted since the beginning of the field, right? I mean, Turing, in his first paper, arguably the first paper on AI, the paper that introduced the Turing test, and which also famously introduced the idea of building a machine that grows into intelligence like a child, or that's taught like a child, emphasized this idea of basically starting with as little as you can build in. Little mechanism, little knowledge, lots of blank sheets. But we've learned now, and this is at least in the work that I do, a lot of the inspiration comes from developmental psychologists and developmental cognitive neuroscientists, like the people you see here: Liz Spelke, Rebecca Sachs, Alison Gopnik, Laura Schultz, Hyo Guan, who was a student of Laura's, also worked with me at MIT and is now recently tenured faculty member here at Stanford and one of the participants in the High Center. And if you look at them and many others in the field, they've shown us all these ways that the starting state and the learning procedures are much more sophisticated in their structure, their content, their mechanism than we might have thought. There are basic core knowledge systems, as Spelke has shown, for objects, agents, and places. Rebecca and others have shown how the brain systems that underlie these are largely taking the same shape, even in very young babies just a few months old. Or Alison, Laura, Hyo have shown how the learning algorithms, we heard about the child as scientist in the morning, right? And I think some of the work that Dan told you about is starting to take steps towards this. But the ways children build models, do experiments, form theories, get into an experiment theory building loop like a scientist, go way beyond what we've been able to do so far in sort of traditional machine learning driven AI. So I want to talk about the ideas, the formalisms that we've been trying to develop to capture these ideas, like what we call the game engine in the head, or the child as coder, or the child as hacker. Okay. Now we do this in our work in the context of several technical tools. One is the idea of probabilistic programs and probabilistic programming languages. These are new AI programming languages which integrate the best ideas of multiple eras of the field. Surya gave a really nice history of the field, which talked about Bayesian approaches as well as neural networks. But I think, and both of those are really important in the kind of work that we do. Bayesian inference for reasoning about unobserved causes from sparse, uncertain data in hierarchical probabilistic models. And Sanjeev formulated that very nicely, as well as, and also how that relates to the neural network and pattern recognition function approximation toolkit. These are complementary and work nicely together. But I think what also gets a little bit of short shrift is the original and maybe best idea in AI, which is symbolic languages for abstract knowledge representation and reasoning. I agree with Yejin about almost everything, I think, except maybe I think that there's more value in actually having underlying knowledge representations that use symbolic languages like programming languages for abstract knowledge representation and reasoning. And I think by combining symbols, probabilities, and neurons effectively, or differentiable programs, then that's a very powerful toolkit together. Another idea is this slogan the slogan I use for it is the game engine in the head. The idea that the very fast, approximate simulation programs for graphics, physics, and planning that are at the heart of modern game engines, and that have been increasingly used to train certain AI systems, especially in the sim to real paradigm, I think can be extremely powerful if you think about those as prototypes or examples of the kind of cognitive architecture, that the kind of common sense core knowledge systems that would be built into our heads, into babies' heads by evolution. So the difference is, this isn't about a sim to real approach. It's about a child who sees an object, sees some objects, thinks about a plan, thinks about a goal, like maybe I can roll this ball and knock those things over, and actually has the simulator in their head, which they use to perceive, think about, predict and make their plans, right? So that's why it's not the game engine as a training ground. The real world is the training ground, but the game engine is in your head. It's the basis of the models. So over the last 10 years or so, we've used these tools to capture a number of aspects of basic common sense in quantitative terms. So with Pete Battaglia and Jess Hamrick, who are now part of Matt's team, core members of Matt's team at DeepMind, and continuing in all sorts of interesting ways that are related to this, we've used these tools to build models of intuitive physics, for example, in blocks world scenarios, to answer questions like, will the stack of blocks fall? And to capture here quantitatively people's judgments about how stable a stack of blocks are. But the same tools can answer many different questions without any retraining or really any training at all. Okay. In this system so far, there was no learning. There's just probabilistic inference running a few approximate simulations in a game-style physics engine. But that can let you answer questions like, which way will the blocks fall? How far will they fall? What will happen? How it will be different if one material is much heavier than another? Working backwards, if something surprisingly isn't falling, can you infer which is the heavier material? Or to do interesting kinds of counterfactual reasoning, right? In some sense, this connects to some of the themes that were raised when we're talking about Judea Pearl's work. But now the causal model isn't a graph, it's a physics engine program, which is necessary to reason about flexible, open-ended world of many objects and complex interactions. There's no single graph that describes how blocks interact. But if I want to answer a question like, what will happen if I knock one of these tables hard enough to knock some of the blocks onto the floor? Will it be more red blocks or yellow blocks? Well, across these scenarios and an infinite range of others, we can capture people's quantitative graded intuitions of more or less red or yellow by the following sort of mechanism. We infer a 3D scene description, an object-based scene description, and run a simulation. That's a simulation of a small bump. Here's a simulation of a big bump. And we just have to run a few simulations, one or a few simulations. You don't have to run a high precision simulation, and you only have to run it for a few time steps to be able to capture people's intuitions on the grain of kind of quantitative precision and probabilistic approximation that you see in the behavioral data. In some particularly recent work, Kelsey Allen and Kevin Smith in our group, and I should say Kelsey is also about to join Matt's group under Jess Hamrick at DeepMind in a few months, just finishing up her PhD. And a core part of that is this virtual tools game, which you can see here. I'm just illustrating a few people playing this game, where the idea is you flexibly have a goal, which is to get the red object into the green region, and you try to achieve that goal flexibly by picking up an object and dropping it somewhere into the scene. And here you can see a few people playing different versions of this game. Okay, you don't have to learn to play this game. You use the physics knowledge that you have of the world, and then you can play any one of these levels, not perfectly, but across many levels. These are just a few of the ones we've studied. And here are some of the within level learning curves. People typically take 2, 3, 4, maybe 5, 6, or 7 trials. It's few shot, if you like, reinforcement learning, but people can learn to solve one of these levels on average in just a few trials, and a simulation-based few shot model-based reinforcement learner using the approximate physics engine that we've talked about can capture pretty well what people do here. The same kind of models can capture and provided actually some of the first quantitative models of intuitive physics in babies. So babies shown scenes like these ones over here, which again, this isn't really like anything that the typical 12-month-old has seen, but seeing just a little bit of dynamics of a few objects bouncing around in one of these gumball machines. And then with an occlusion of either a very short period, but like on the time scales that Aude was talking about in the moments data set, 0, 1, or 2 seconds. In this experiment, you vary the number of objects at different colors, how close the objects are to the exit at different points as they're moving around randomly, and the duration of occlusion. And those have predictable effects on how likely an object of one color or another is to come out of the hole after occlusion. And infants look longer in a graded way when something is more surprising or lower probability, according to our model. So this probabilistic physics simulation engine was really the first model that we had that could quantitatively predict infant surprise. Okay. Bringing things back to the brain, we've together in the last couple of years, together with Nancy Kamwisher and several great researchers in her lab, Jason Fisher, who's now at Johns Hopkins, and Sarah Schwetman who's finishing up her PhD, have identified regions in the human brain that seem to underlie these kinds of judgments, including the predictions that we talked about, but also, for example, invariant representations of mass. This is a paper that recently came out in eLife, where you can, for example, cross-decode across all these different ways of perceiving whether an object is heavier or lighter based on its physical dynamics. It seems that this part of the brain is inferring and encoding that, and it also underlies the kinds of predictive judgments that we saw here. Okay, these brain networks in premotor and parietal areas, it's not like nobody's ever studied them before. They've been previously identified and studied in the context of action planning and tool use. And I think that's, as I hope you can see here, that all makes sense now, in a sense, that, I can tell evolutionary just so stories, and I'd love to try to study these in a serious way. But the idea that brain systems that, originally developed probably to move our own bodies around and then to use other objects as tools and figure out how to use them to move other things around, they now can be taken offline and used in this very, very flexible way. I'd really love to understand at a neural circuit level how these systems work. And to do this, I've been working with a number of researchers, including and especially people in Dan Yeamans' lab. So here, these are just figures summarizing two of the projects that Dan talked about. Damien's work on these hierarchical relation networks for particle-based physics, and Dan Baer and Xiaofei's work on these learned physical scene graph representations. And though we don't yet have direct evidence that the brain works this way, these are at least somewhat plausible models, especially when you confront the challenges that Dan was talking about, like the fact that graph networks are not exactly like neural networks, but you have to have some way of rendering them into a fixed finite size neural population. But this is the research program. And what I'm showing you is the top-down perspective on what I think, as you saw, is the bottom-up perspective before. So the optimist in me is that these perspectives can converge. Though we don't have evidence for those kind of models yet as being in the brain, we've identified where to look with fMRI, and the next step now is to see if those models actually can describe the encodings there, for example, and then maybe even the neural circuitry. But one example of this kind of approach, work that Ilker Yildirim recently published in Science Advances, is just another idea of basically using a neural network, a deep neural network, that's been trained to invert not a physics program, but a graphics program. And he showed that when you apply this to the well-known face patch circuitry that Doris Sau and Vinberg Frewald have studied in macaques in inferotemporal cortex, this kind of neural inverse graphics program provides really a strikingly good account of, for example, the patterns in similarity of representation of faces in different viewpoints and different identities. Here's the efficient inverse graphic network of Yildirim, and it does a much better job of accounting for multiple stages of representation in the primate brain than, say, VGG face, which is one of the standard state-of-the-art open deep neural face models that was trained not to invert a graphics model, but to do classification. So in some sense, this also gives a different interpretation of the function of the visual system, something potentially more generally like inverse graphics. Intuitive physics has been used and recently in several, these are just several collaborations we've worked on to try to put intuitive physics into robots. Some of these systems do various kinds of learning. So for example, Yunju Li's system in the lower left that's kind of making this sushi rice uses a very similar kind of hierarchical relational graph system to the work from Dan Yeamans' lab, but then uses it for model predictive control. But the systems, for example, that Marc Toussaint built that like humans and even like some other animals, smart animals like crows, can learn to use tools that they've never really encountered before in flexible ways, even to use, for example, a tool to get another tool, or Nima Fazeli's work with Jiajun Wu, who's recently joined Stanford as a great assistant professor in computer science, building a system that can learn to play Jenga, or Yuanming Hu's work on using soft body physics engines to learn to walk. There's relatively little learning here, or very, very simple focused model-based learning. And again, I think this represents the more sort of top-down structure-driven approach to how we might use intuitive physics in robots that can flexibly engage with a range of tasks that are not much like the experience they've come before. I just want to leave you with two highlights of where I think the future is. So one is, I think to really make this approach, go to the moon, it's going to need some rocket boosters. And for this, I've been collaborating with my longtime colleague, Vikash Mansinga, who runs MIT's Probabilistic Computing project, especially the work of Marco Cusimano Towner, who recently got his PhD there, based on the system Gen, which is one of the newest state-of-the-art probabilistic programming languages. Really think of it as a AI programming platform that really nicely integrates probabilistic, symbolic, and differentiable, or if you like, neural network modeling and inference. This is an open source platform. It's, I won't go into the details, but it's Julia-based. It also sits on top of PyTorch, and it really gives us ways to build flexible, scalable, very efficient, real-time generative models and a range of specialized inference programs that can let you do, for example, take the ideas of common sense object systems, but also agent systems and places systems. These are sort of the three classic Spelke core knowledge systems, and take game engine inspired symbolic geometric representations of scenes, but now across very different scales, ranging from abstract symbolic scales to fine scale 3D structures and many things in between, and do real-time probabilistic inference over these. I think that's what's going to allow us, for example, to really make good on this as a approach to scalable AI. I'll skip, because I'm just about out of time, how we're using this in the context of action understanding, but we can come back to this in the discussion. I've mostly focused here on intuitive physics, but understanding, for example, what makes a scene like this, how you understand what somebody's reaching for and that somebody else is trying to help them, versus a scene like this, where you understand that what somebody's doing is the opposite of helping, right? We think that these kinds of when we already have preliminary examples of these kinds of probabilistic programming systems being used in a multi-agent context with generative action programs and agent models, where the agent can basically try to maximize its expected utility based on its expectation of another agent's expected utility. That's a simple version of helping, where you make it a negative dependence and then it becomes hindering. This is a way to try to do the kind of action agent-based scene understanding that we saw, for example, in the Wernicke and Tomasello videos. The last direction I just want to talk about is learning, which is, if common sense is based on these kinds of simulation programs, then learning common sense has to be something like a program learning program. So we think of this as, what I sometimes call the hard problem of learning, because unlike learning in a neural network, it's not just about, there's not a smooth error landscape that you can do gradient descent on. The space of programs is much more complex. The search problem is much harder, yet somehow children solve it. Starting a few years ago in our group, we've been working on something that we call Bayesian program learning. So, for example, in the thesis of Brendan Lake, he developed together with Russell Kudinov this omniglot data set, which for us is, for many people have used it as a kind of one-shot or few-shot concept learning domain, where if you look at all these characters in many different alphabets, each one represents a visual concept, a simple one that you can learn from one example. But the way we approach it is as a simple warm-up problem for program learning, because every one of these concepts can be described by a generative probabilistic program, something like a drawing program or an action program for how you put ink on the page in terms of strokes and substrokes. And that makes a template for how you would draw new characters. And then perceiving or learning a character from one example is a kind of Bayesian inference, running that program backwards to infer the evaluation trace that led to one example, and then you can sort of rerun it to produce, render, imagine, and classify new instances. And this idea of Bayesian program learning is one that we've been applying in a number of different settings, going beyond handwritten characters like 3D shape programs or programs that can interpret images, or even kinds of reinforcement learning simple Atari-like video games. This is from the thesis work of Pedro Civitas, where he's shown that the idea of Bayesian program learning and then using that in a sort of a model-based planning approach can learn to play new Atari-like games very, very quickly, hundreds of times faster than even the best deep reinforcement learning systems, and almost as fast as a person. So where this leaves us, though, is still with much harder problems of essentially program synthesis. To me, I think the rocket boosters that we need for learning programs is best encapsulated in this phrase, the child is hacker or the child is coder. Hacker is, around MIT, we're thinking of the good kind of hackers, the ones who just spend all their days making their code more awesome. But you could just think of any really, good creative software engineer. Whose job is to produce code. What are all the activities of coding? All the ways you make your code better on a daily basis. So tuning parameters is one of them in existing code, right? That's kind of the coding version of what we do when we're running stochastic gradient descent or backprop on a fixed neural network. But there's many other activities which are structurally modifying the code, adding functions, extracting functions, debugging, finding errors, profiling, refactoring code to make it more generalizable, maybe more efficient, more elegant, adding new types, writing new libraries, writing whole new languages. And we think all these activities of coding have analogies in children's learning. And so if we want childlike learning algorithms, then we need coding algorithms or automatic program synthesis algorithms that do these kinds of things. Now, we're very far from doing that. And this childless hacker TICS paper just kind of sketches out the idea and makes the proposal. It's sort of a white paper. I'll just leave you with one example of another recent PhD thesis from our group. This is the work of Kevin Ellis, who just graduated this year, and he's going to be starting next year as a assistant professor at Cornell. In the meantime, he's working at a startup called Commonsense Machines, which came out of our group also, and is trying to explore some of these ideas in some AI sort of model building context. That's a story for another time. But what Kevin did in his thesis work is built the system, among other things, called Dreamcoder, which is, you can think of it as a system that doesn't just learn to write programs, but it learns simple programming languages to capture a domain of learning. It does this with a kind of wake-sleep learning in what is often these days called a neurosymbolic framework. So the basic things, at the heart of what it learns is libraries of coding primitives that then let it write new programs more quickly. But it also learns a neural network to guide the search. And it jointly bootstraps through two different kinds of sleep learning phases, the symbolic program library, as well as neural networks, which represent a kind of procedural expertise that help to guide the search for new programs. And just to illustrate this on some kind of more graphical examples, there's many different applications of this system. But like, let's say we want to learn to make various objects out of blocks or learn drawing programs. So for example, we can start off with a very simple minimal language for drawing, like logo, basically, right? Where you have a pen, you can pick it up and put it down, you can go in a line, or you can turn. But then we can learn a library of higher level drawing primitives like circles, semicircles, spirals, polygons, or higher order ones like take any shape and repeat it radially symmetrically some number of times, okay? And then that now lets us learn to draw many new shapes that we couldn't draw originally. The neural network is trained on these simulations that are drawn from basically there's a probabilistic generative model that's this learned library. So we draw over iterations, we simulate random programs drawn from our growing library. And so over the course of learning, because the library gets more complex, the random simulations or the dreams become much more interesting. And that provides much better training data for the neural network, which helps it solve more problems, which helps it learn yet more new good primitives. So that's the positive virtuous cycle of bootstrapping that you can see in this algorithm. We think that's one way to start to capture some more interesting ideas of children's learning. Okay. There's a lot of other cool things like using this to learn languages of vector algebra and physics, or even learning basic functional programming languages. But check out the Dreamcoder paper on arXiv if you want to see more of that. So just to conclude, what I've tried to sketch here is both the toolkit we're using and a roadmap for how we might start to fulfill AI's oldest dream, building a machine that grows into intelligence the way a person does. And from the science side, really thereby come to understand better how our own minds are built. And it starts from revisiting the classic questions that come up in any approach to learning, which is what do you start with and how do you learn the rest? And recognizing from multiple decades of developmental psychology and cognitive neuroscience that human brains really do seem to start with a lot of structure, and learning procedures have to be, or we have a range of learning procedures, including things which are something probably like neural networks or like stochastic gradient descent in a differentiable program, but also much more structural kinds of learning and inference as we see in probabilistic programs and program synthesis methods. And when I talk about a roadmap, what I mean is something like this, okay? And I think this is where especially the work I've been talking about meets up with what Yejin is doing. Multiple phases of knowledge that start with that 1.5-year-old stage and then go into the next key stages of learning. So what's the next big stage after 1.5? Well, it's basically 1.5 to 3, when the most important thing that every child in our world learns is how to read, or language, and then how to read, right? And once you get that, then you have the stage of 3 on up, which is using language to learn everything else. First by talking, asking questions and answers, and then by reading. And that allows you to tap into all the knowledge that humans have built culturally that accumulates across generations. That's the real singularity. I think that's the basis for being able to build machines that humans can interact with the way we've always interacted with each other, in a true human-centric way. Machines we can talk to, trust, and teach. And I think building, the kind of human-centric AI that HI is all about. And when I say this as a roadmap, I mean this quite seriously. I mean that by seriously studying each of these stages of children's cognitive development, trying to draw the kind of reverse engineering insights that we've tried to do in the earliest stages in babies, but doing that all the way along, building up with the engineering toolkit and the science together, I think that really is our best hope to build the kind of AI that we all would like to see. Thanks.
Thank you very much, Josh, for that integrative panorama. So at this point, I'd like to ask all the other speakers, Sanjeev, Yejin, and Aude, to come back and join us for the panel discussion. And I'd like to remind our audience that you can submit questions for our speakers on the event page of our website. Okay, I think we've got everyone back and live now, so let's start at it. As a prelude remark, Josh already observed that in some sense the morning speakers were more of a lump, in that, I mean, if I very crudely group them, in some sense they're all happier with a learn forward from pixels perspective to life, whereas the afternoon speakers are a much more diverse crowd. But we really do hope and believe that there are a lot of different perspectives and a lot to learn in different ways, and actually understanding intelligence, both human intelligence and how to build it into machines. So I thought I might ask first Sanjeev a question relating to the first part of your talk, but it's a little bit of a tricky question, but I'll try you on it and see if you have a thought about this. In the morning talks, our morning speakers basically said, neuroscience is useless for understanding how learning works or learning algorithms, right? That we just can't really see the details of the learning algorithm or come up with anything useful from what we can do with neuroscience. So if we're going to make progress in learning algorithms, it looks like it has to come from artificial intelligence. And of the three motivations you listed, so basically the second and the third ones were both related to learning algorithms. The second one sort of more narrowly on optimization methods, and the third one as to what we actually need to understand how we get flexible interactive agents like human beings. Do you think, right, so in the neuroscience context, there's been lots of discussion. People say that there doesn't seem to be anything like backprop, but there are certain kinds of feedback loops that are going on. Do you think there are possibilities for a theory first perspective to help us get more insight into how human learning works, or is that too much of a leap to hope for?
So I think one insight that we got out of some of the theory we did in the last couple of years is that you should the gradient-based learning that we do is at the parameter level, right? And and what we are interested in is the end-to-end functionality, the functions, and that seems to be some very different process. So, and you can't really infer the properties of the latter from the former. So right now we just understand that those can be very different, and you don't go in an easy way to understand the trajectory of the end-to-end function. So I guess my question about the neuroscience would be that the data is, as you say, very low level, and it's very fragmented. There's all kinds of things going on, and you see bits and pieces of it. And so indeed, yeah, what we have an intuition about is the end-to-end function that's going on. And the mechanics of it, it's not clear that that's so important. I mean, there's some local update and there's a network there, but not clear that that should be very important. So maybe we're on the right track and sort of inventing our own architectures.
Is possibly part of the answer to that the direction that Josh, you were heading in on wanting to emphasize the structure that is present in the brain. So rather than, I guess, most of modern neural networks, deep learning, well, there's some structure that networks, but in some sense, the role of that is minimized and the role of parameter learning is maximized.
Yeah, I mean, I think there is a connection, and I think it's one that I'd love to get a theorist perspective on, because I mean, there's again, Sanjeev mentioned this also. There's a long tradition of learning theory that shows that if you want to generalize in strong ways from small amounts of data, you have to have some kind of inductive bias or something built in. And the question is sort of in what form is that built in, or are there ways that in a meta learning sense you can get other kinds of data that can inform what's going on? But one idea, I mean, here's a very relatively concrete theory question. I know actually we've talked about this with Surya. I don't know if Sanjeev, we've talked about it, but there's a thing that we see, in the, let's just say the deep learning community sees. I see this in some of the deep learning projects I've worked on, where when you take a complex deep network that achieves some state of the art or great performance on maybe an engineering task or on some brain modeling task, the training matters, but it doesn't matter as much as you might think. If you take the architecture and just kind of randomize the weights, so start off with small random weights, often it kind of still works, not as well, but often still kind of works. And networks, if you compare different architectures with their initial weights, there's often the same relative performance. The ones that are really good after training or better after training were also better before training. And one more thing that we see, and I've seen this in vision projects we've worked on, as well as language projects. Like there was this project that was mentioned earlier by Martin Schrimpf and Ev Fedorenko, which I played a small role in that project on using GPT and other transformer models for modeling language in the brain. We see the same thing there also, which is that if you take, again, an untrained sort of random weight network, but you do just a little bit of training, like on the last layer, like you build a linear decoder, that often works pretty well. So I wonder, what is the possibility, or what are the prospects for an approach to understanding how brain development and inductive bias might work, where most of the inductive bias is in the architecture, with a little bit of learning kind of at the end. So you don't need to do backprop if all you're doing is building putting a single layer on at the end, or again, it might be different brain networks that effectively act as a maybe very structured layer looking back at another one, but the amount of learning could be local and limited, and there could be a lot of inductive bias in the architecture. Can we understand theoretically like why that often works pretty well? Does that resonate with you guys at all?
Yeah, so I guess I'll mention a few random things and see if it works. So there's this study of over-parameterized nets, and one of the things people have studied are these neural tangent kernels. Did you take an architecture and take its infinite limit in width? And that's sort of like what you're saying, that you're basically training the last layer in some sense. And there's a strong inductive bias, which is a neural tangent kernel for that architecture. And those actually do reasonably well. And these were always called, I mean, these are related to what the Europeans used to call liquid state machines. They've been studying those for several decades.
But these could be, but those are like where there's like basically random weights, and even like a random.
Right. So what happens is that when you go to the infinite limit, the training is basically very minimal as well.
Right.
Basically you're seeing something related to the architecture, not so much training.
It's interesting that again, like the transformer architecture was clearly a big step forward, right? Even if it's not enough, it's clearly a big step forward. And GPT has some nice architectural properties that are different from the BERT style models. And it's interesting that maybe what we see going on there is like a cultural evolution, recapitulation, or analog of biological evolution, right? Where like the culture of deep learning driven by the massive energy of the tech industry and all of what all of the things you're saying we want from our technology, leads to a process, again, it's a kind of code evolution process that produces architectures that have really interesting properties. And maybe that's kind of analogous to what biology did, where again, a lot of the work is being done by evolution, coming up with a certain architecture which has certain inductive biases baked into it.
So I want to actually make a quick point about that. So what you call architecture actually comes with an algorithm, training algorithm.
Right. That's right. Just as in biology, right?
Yeah.
You're saying in biology, they're both
right.
exactly.
Yeah.
Right.
Yeah. So there's like a simple paper, like a cute paper we have out as well, and like the difference between convolutional nets and fully connected nets. Like, how do you explain that convolutional nets are better? And you cannot do it by traditional learning theory because a fully connected net contains a convolutional net, right? You could always train it by ignoring some of the connections and enforcing weight sharing. So somehow the algorithm, training algorithm plays a role in the difference. So now actually we have some theory that shows it. But so yeah, there is definitely an algorithm at the back of your mind already when you talk about architecture.
I wanted to dive in. Yeah, so Sanjeev, yeah, we've also looked at these neural tangent kernels, and we actually showed that in narrow networks that are used in practice, if you train for a little bit, you have a trained tangent kernel that picks up a lot of important features and data, that then if you learn with that one, you outperform the usual neural tangent kernel quite a lot. But so I wanted to go back and ask a question in general, I think an integrative question about learning, right? So on the one hand, we've been talking about common sense learning, Yejin and Josh talked about that. And then on the other side, we've been talking about self-supervised learning. So these are kind of two related questions. I'll just ask the first one for now. A key theme and arising in learning powerful representations that spans multiple talks is sort of self-supervised learning without labels, where you try to predict one part of an object from another, like predict a word from the rest of the sentences or predict different views of an image, whether they're the same image or not. And in Aude's talk, whether three action sequences were, which one was the oddball action sequence. So why is it that these simple auxiliary tasks, self-supervised tasks, actually yield powerful representations? Can there be a theory for that? Can we have a guide the rational design of auxiliary tasks for bootstrapping powerful representations? From a neuroscience perspective, I find this very interesting because the first thing the retina does is parcelate the world into 20 different visual representations. For example, one of them is black and white and one of them is color. And we know from AI work that predicting color from black and white yields somewhat powerful representations. So maybe evolution figured out a way to parcelate the world into different subparts, and then it predicted the parts from each other in a very powerful way. And what we haven't quite figured out is what should we predict from what else, right? So I just wanted to seed that and see what you think.
We go to Aude first for some thoughts.
Yeah, Aude, this was inspired by Aude's talk, actually.
Yes. So to me, if a model is self-supervised or whatever literally the learning method you use to build your model, as a cognitive scientist, I will ask the model to show me beyond the performances of recognizing, for instance, object, is actually the error and the mistake that the model can make. So what we do is we go by our life by actually comparing something with something else and so on. So in a very simple way, we have those distance metrics, and the distance between things represent the type of mistake we do. So we could take an apple for an orange. So there's a long metric that can characterize the mistake. Now, one of the open question in neural network, whatever the learning method you use, is let's say you have two networks with very different way to learn that produce the same sort of mistake. Does this mean that the representation they use is the same or not? And a lot in human cognition, we have this hypothesis and assumption that when the mistakes are very similar, then the underlying collection of representation of calculation are also similar. True or not, those are assumptions. But I see with the very fast development of a whole species of neural networks, that we could be in cases where the output looks like something we could do. The range of mistake makes sense. Take the tiger for the cat, that makes sense. Take the tiger for the car, that does not make sense, the kind of, but have different representation. And that will be very informative to show how artificial networks with very different principles end up in the same same result. And that will be a way how AI can actually make cognitive scientists back to think.
Interesting. Yeah, that's interesting. I just wanted to contrast that with like the second question I was thinking of. And I do want to return to the self-supervised learning versus common sense reasoning. So the second question was about common sense reasoning, inspired by actually Yejin's talk. So I loved, Yejin, your example of visual question answering data sets, right? Where, you know, the professor doesn't teach and the professor just gives you a whole bunch of multiple choice questions and gives you the right answer, right? And then can we learn structured representations from that kind of a professor? And I sure couldn't, and I don't think humans can. And so you said we need to evaluate machines more generatively. We need to teach concepts more directly. And so what do you think the most promising pathways are there to doing that? Is self-supervised learning up to the task? Is it not? You know, what do you think about that?
Yeah, so I was going extremely fast over that slide than many others. But my current thinking is that self-supervised learning is a really important and powerful substrate to have. But in answering your question, I would like to also throw a theory question to Sanjeev, sort of going with, you know, all your vibes about, you know, asking Sanjeev some like interesting theory question, because when you look at these self-supervised language models, it's quite curious why GPT-3 can write really amazing quality life blogs. So, you know, there's this Berkeley kid who used the GPT-3 to produce a lot of life blogs, life advice, I meant. And I've done some of these experiments myself, and it's unbelievable how good the coherence is. There's like initial planning about what I'm going to tell you today, and you know, it maintains this long-term coherence. It's able to make some book recommendations relevant to what it's saying. I go ahead and check all these books, they exist, authors are correct. And then I went ahead and checked that it didn't plagiarize anything, and it did not, because I know it couldn't, because the way that text is generated is through random sampling. It's not entire random sampling, it's either nucleus sampling or temperature sampling. But in any case, it's curious why it's so good at seemingly harder tasks, and then it cannot do something so simple like, you know, common sense queries, and then, you know, you're supposed to say something obviously true, but GPT-3 spits out things that are so untrue and confused. So in some sense, it's very easy to break GPT-3 with much simpler tasks. And on that note, for example, we cannot still do paraphrasing or much easier lower level task that we would assume that someone who can write that nice blog post should be able to know about everything in language. But on a similar ground, it seems that machine translation is much harder, easier task compared to reading comprehension. And even the way that we currently, quote unquote, solve machine translation or reading comprehension is by converting everything into sequence to sequence models, under which it almost looks a little bit like a self-supervised learning. It's not, it's supervised, but just the way that it's all about, you know, predicting the next token correctly. The objective function that seems being recycled by all these powerful transformer-based sequence-to-sequence models are, again, somehow formulated technically very much like a perceptual task. So when I was presenting this perception system 1 and system 2 reasoning, even for such higher level cognitive task like machine translation and reading comprehension, we move that into perceptual level stuff, and then that's how we do today. And it seems that this is really curious whether there's any theoretical way to say something about why writing blog posts is so much easier than being able to learn trivial common sense knowledge that every human knows about. And then I do have a speculative cognitive thought. That's not theoretical, but more practically speaking. I'm drawing inspiration from cognitive science in this regard that Josh talked about these core concepts. Is that the right word? Speck has core cognition concepts, like the way that humans learn about concepts, treat objects differently from actions, which are different from maybe forms, and time is different, and location is different, and the functions are different. These are all different fundamental concepts. Today, we treat everything as just same vector. And it seems that that's sort of the key challenge. And when I think about concepts, basically it's the ability to abstract away what's the sort of stuff Josh is doing, for example, and Aude was also presenting, where there's some like abstraction that is happening, but I don't know how far we can push by just using only one method. We might need to just broadly search, which might require really rethinking about the current paradigm of learning, whether supervised or not. I feel like they're both very narrow, although I love self-supervised learning.
Okay, should we get some comments, perhaps starting with Sanjeev?
Okay. Yeah, so we've been studying self-supervised learning in my group for several years. I think Chris was very influential in helping me in the early days. Yeah, so I think the way I phrase self-supervised learning is more generally that there's task A and task B, and that you learn to do task A and it helps you with task B somehow. And the distribution may be very different and so on. So that, in a sort of black box way, will not happen very generally. I mean, unless the tasks and the distributions are fairly related. So it seems quite clear with a few toy examples that the inductive bias of the architecture is very important, what Josh was referring to as well. And I guess, yeah, Surya also referred to the architecture. So, and the architecture, I think, includes the algorithm, the training algorithm. So those are some of the basic things to say. And so then in terms of what we can do, I mean, saying something about what happens in training 100 billion parameters is currently a very difficult challenge for deep learning theory. So we have relatively toy models, but using those, you can sort of start teasing apart these things, like I indicated for language models, like, I mean, there's some benefit to just, GP2 is a better language model than GPT-3 is a better language model than GPT-2. So you can see in some toy settings that epsilon, how far it is from optimum, helps in the task B. But then to answer your other question, why is it bad on some things? It's possibly true that learning the distribution, which anyway, to begin with, Chomsky's objection, all that. I mean, it's a shaky assumption that language has a distribution. And so if you're just phrasing your task as learning a distribution or predicting, then maybe there's only a limited number of things it implies, and it doesn't imply some of those other skills you want. Yeah, and those are all great questions for theory.
Can I comment on that? Yeah, I mean, that's along the lines of the way I think about it too, right? I mean, I think for many self-supervised algorithms, you can think of it as like learning a distribution, right? Like people who liked graphical models or Bayesian methods should be very happy with these, right? I mean, GPT is explicitly framed in that way. It's a lot like, the way, like, when I got into the field, the way we would approach unsupervised learning from a graphical models or Bayesian perspective is we define some latent variable model where there's some latent structure. I'm going to try to diagram it, some latent structure with some prior, and there's some arrows coming down to the data. And, classic probabilistic language models, whether it's hidden Markov models or probabilistic context-free grammars, can all be framed in that way. And you could view what you're doing in, let's say, self-supervised learning in GPT or BERT. They're kind of variants on this. They're not exactly the same, obviously, and they're not exactly what I'm saying, but GPT is close to this, is like, assuming maybe relatively little explicit structure of the latent variable space, maybe a lot of implicit structure, which we don't fully understand. But, you're basically, you're training a generative model. And by training many different, predict this condition on that, and this predict condition on that, like each word on any possible previous context, or in BERT, like each held out word or small chunk of language condition on everything around it, right? Like that's, I think mathematically one should be able to show that is similar to, maybe even in some cases exactly going to be the same as, as maximizing likelihood in a traditional unsupervised learning sense. But it has an extra bonus, which is that it's not just learning the latent structure and the prior, but it's doing a kind of amortized inference, as Noah Goodman and others have called it, right? Like, because it's learning both a latent space that assigns high probability to data, and an encoding or recognition model that can estimate those latents from some other data. And maybe, and in some ways, like there's some nice work. I'm thinking of Richard Turner's group, I think, has some work on this. Many people have looked at this, where you might see meta-learning algorithms and other kinds of algorithms like this as basically like they're jointly learning a good prior, but also sort of an amortized posterior, and you're learning a latent space that has multiple good properties. And then maybe what makes some architectures and algorithms better than others is not just do they capture the structure of the domain in some implicit way that can support good predictions, but do they, are they running the inference network in the right direction? And that, clearly, I would say, we all say that's why GPT, or that would be related to why GPT is so good at generating long-range coherence, because that is the direction, in forward prediction, that's the setting it is trained to do that. So, maybe in some sense we shouldn't be surprised by that. It is, just like in earlier work with GANs in vision, it's surprising how much you can capture in these learned generative models and how much they can look like the real world, even things you haven't seen before. But also, just like what you were saying, Sanjeev, and I think what cognitive scientists would say, well, in some ways, going back to Chomsky, we shouldn't be that surprised that while there might be statistical structure to language or to images, right, that's different from it's maybe a consequence of the structure of the world, and the cognitive systems we build, having those kind of predictive statistical models are probably an important part of our real-time processing and how we use our knowledge, but it isn't the same as the knowledge, right? It's not the thing that supports counterfactual reasoning, imagining things that are vastly different from anything we've ever seen before, whereas the kind of common sense core knowledge that Spelke and others have studied in infants might be that, right? And then some of the things that we build when we build more, at least my view is when we build more layered, structured, symbolic representations in natural language and others beyond that, also, again, give us the ability to think about and talk about and learn about things that are very different from our experience. And
so we maybe give Aude a chance.
Sure. Yeah. Sorry. I started going into yeah. Right. Good.
Like I was just listening to Josh.
Well, I'll just say one more sentence and then shut up, and then it just closes off, which is just to say, imagine if we could do self-supervised learning, but with a more structured latent space, basically, that has the kind of common sense core things. That might be a way to get the best of all of these worlds, and maybe would lead to systems that that would have more of the properties we're talking about. And maybe that's what Comet is even in some sense starting to do. I'd like to understand it better there.
Okay. So is there anything you would like to add, Aude, or should we go on to a different question?
Different question. I was really listening, going into what was said.
Siri, do you want to?
Yeah, sure. Let's stick on this topic of common sense. So it's easy to point out examples of common sense, right? And we all kind of have a common sense notion of what common sense is. But it's perhaps a little bit more difficult to come up with a precise objective function that one could optimize to teach a machine to exhibit common sense. And so the question is, how might we as a field work towards that goal? I mean, Josh touched on this a little bit at the end of this talk in terms of program learning programs. And so can there even be an algorithmic optimization-based approach to learning common sense? Or might evolution have found some more common sense approach to imbue us with common sense, whatever that might be? And how might we exploit that to teach machines common sense?
Yeah.
I think Yejin and Josh probably have the most to say, but yeah, go ahead, Yejin.
Yeah, I love this question. It's really interesting, almost a philosophical question, but practically speaking, it is true that it's really difficult to define common sense knowledge, and it's really surprising how much we actually know as common sense knowledge, as well as how much it actually does not really align exactly. So you and I could have a different quote unquote common sense knowledge. It's aligns well enough so that, we probably will not get into fist fight anytime soon. But it's similar to language, though, in that, what is the true definition of language so that you can really define and incorporate everything that people ever say? Well, today we kind of implicitly define it by just, here's this bunch of text that people spit out, and let's optimize for the perplexity during training or log likelihood, whatever. So similarly, this is how I view, except that the challenge is that there's no natural corpora where people spit out common sense descriptions, which is why we had to start with this atomic knowledge graph as a symbolic small subset of common sense that a lot of crowd workers seem to share. But similar to language, also when we write papers, reviewer to always do not understand our perfectly written paper. There's nothing confusing about it, but they didn't understand. So that's how I also see common sense is like that. People might have a little bit different interpretation, but that's okay. And that shouldn't deter us from studying this as a scientific topic, just like how it's okay to study language, even though reviewer two never agrees with us. About like, so for now, I didn't have any better way to do this other than directly optimizing for this atomic corpora for the time being. But what's wonderful about it when it's mixed in with self-supervised learning on language itself is that it's learning significantly more than what I could ever imagine. So when giving this online, giving these talks and then doing online demo, oftentimes I was given like adversarial examples and I would tell the audience that, oh, this is not going to work. And then I try anyways, just for your viewing pleasure. And then it does do better than what anybody would have expected. So this happened multiple times. I'm not saying that this is a perfect system, but it's very interesting how much it can generalize. And then I'm seeing that the stronger language model is, the faster the generalization actually happens. So it's now I'm starting to speak things that's not in public space yet. And that's very exciting, but I don't have, ideally, I really wish that we didn't even need atomic or anything and some magic arises from neural network to figure everything out. But I do wonder whether it's even reasonable wish to have if we only have current learning paradigm set up either for optimizing likelihood on a lot of raw text or solving this QA problem right. I think we somehow need to have an entirely different objective function, which might be even harder to write than writing the objective function for common sense. So I don't really have an answer other than some shreds of speculative thoughts.
Yeah, go for it.
Is that what's very good about common sense is that the concept is so elusive that we basically don't know how to give an operational definition, that a lot of people are going to use it and do things in a different way. That's very good. There's going to be a lot of the word used. I don't know how to define it. It might be defined depending on the task and so on. But the way I think about it is it's too far. I don't know how to do it. So I need a smaller goal, except that the smaller goal is enormous itself. It's the notion of analogy. We always speak and see and think about analogy. And analogy is a space of possibilities. You can have analogy in space, in time, in concept, in mathematics, in relating colors and so on. So analogy itself is a huge research endeavor. I find very interesting that we were talking about GPT-3. It was based on an enormous amount of learning, but it can perform a very simple level of analogy with one or a few short learning. So analogy is like if you say ABC is to PQR, what's ABD is to PQ, and you have to finish it up. And I think analogy is a fundamental things to model. Go ahead, Sanjeev. I'm done.
Well, I can go next. Okay, so let me follow on with another question.
Can I say something about common sense before we leave that topic?
Josh, you had a concrete approach in terms of programming programs, but
well,
yeah. How would you
I just want
function to optimize common sense? That's the question.
Well, so I just wanted to say, I think I'm more of an optimist, I think, about, I mean, I hear what Aude is saying, and people use the word common sense in all sorts of different ways, but I think there actually is a core meaning behind both the classic way it was used in earlier AI and the way Yejin is using it and the way I was trying to use it. And I think we can, and I think what Aude is saying too, and I think we can work on that. It's something like, you know, common sense knowledge is like all the things that we all know that nobody ever talks about. So, right, it used to be common sense was like all that you need to know in order to be able to read the newspaper. The newspaper never writes about it. It's just what the background knowledge you need to know to read the newspaper, or maybe to read Wikipedia, right? And it's why it's hard to get from data, because nobody writes about it, so you can't just mine it from lots of text. The Spelke or developmental approach, the infant approach, is it's like all the stuff you know before you know how to say anything, right? But that early language builds on, and it's kind of in there, especially like in syntax and semantics of verbs and how phrases are put together. So, like the word the word object or the word agent, those are common sense concepts, but they're not actually words that young children learn, but they are there in sort of the way nouns and verbs work, right? For example, or common sense notions of space and time. Those are also things that verb syntax and semantics, for example, the work of Beth Levine here at Stanford is really the seminal work showing this. It's sort of in there in how we learn about how verbs work and meaning form correspondences. So what that suggests again is it's sort of like, basically think of this common sense as multiple stages of knowledge, starting with what babies have, and then what you have when you first learn language, and then what that comes to enable, which are like basically building languages of thought. It's the stuff, as Steve Pinker calls it, like the stuff of thought in his book of that name, right? It's not the stuff you talk about, but it's the stuff you need to know to form new thoughts, and then to form new sentences, and then to use those sentences to form yet more complex new thoughts. Yeah. So there's not really a metric that you optimize other than basically trying to solve a bunch of problems of the right sort, and then building whatever is the language of thought that supports flexible, open solutions to that flexible, open-ended class of problems, right?
Yeah. Let me ask a question to Aude, which isn't exactly common sense, but sort of heads in the direction, well, of some of the topics that came up of having prior models and of the world, right? So you emphasized these 3-second activity scenes and at least what I took away, that you primarily motivated having these sort of 3-second snippets in terms of, humans responding in the natural visual environment, that they wanted to get a quick snippet of things. But I was thinking in my head, well, so there's an obvious advantage to seeing some movement rather than just a static scene. You obviously get this enormous amount of extra value from seeing a little bit of movement in there. But beyond that, is a lot of the secret of the effectiveness of these 3-second scenes not sort of the human hunter on the prowl or something, but it really has much more to do with humans have these really rich models in their heads, and as soon as we've seen a second or so of video, well, we can predict backwards and we can predict forwards, and it's much more a story about our very good models of the world, both from priors and learned, that's going on there.
Well, the 3-second is just a number in order, if you want to train a model. What we were looking after is that the way our brain conceptualize the world is there's a certain dynamics to it. So if I want to pick up an object, it takes some time. And there's a lot of the activity that are meaningful to us that unfold within a few seconds. So then 3 is just an average.
Sure.
And the thing we observe is that if you train a model on shorter or longer video, or then if you train on on shorter video, you will miss information. But on the sort of 3 seconds, there is enough information in order to develop robust features. And also it's the kind of this average length of short-term memory, or things you do, you put in memory, you think about something else. So we have a big time, time module over here, and it's at several scales. And it was something that just make our model works much better. It's a good number.
It seems like a magic number, though. I mean, in a good way, right? Like people have proposed 2 or 3 seconds as a magic number all over. That would be an interesting paper to write. I don't know if anyone's written that paper, but I'd love to see, what is it about, like, the length of a sentence, the length of an activity, the length of a professional football play, or even a basketball play. There's something about, like, the brain that makes that the length of human activity at the micro scale, or at the basic kind of single sentence level, right?
The autocorrelation of the movement of prey, the time it takes to turn, and while you're chasing it.
Well, yeah, I mean, for mammals at least, maybe. I think they're faster, but but at the level of it's easier for me to think of things like sports, whether it's baseball or basketball or football, because they kind of unfold at that time scale, but that's I don't go hunting, but I don't know. But, yeah.
Well, the other thing is the human brain will have certain buffer related to things you hold for a few seconds. And if you want to remember something after 20
the remembered present, about
after, let's say, 30, 40 seconds, it's another structure. And those are neuroscience results.
Yeah, exactly. There's something fundamental.
It's like at some point you switch.
Right, but yeah, it seems like there's something fundamental about the fact that we're talking about human activity. So it's like the time scale of human activity planning and execution is going to then turn into the time scale of where perception is most meaningfully.
Yeah.
And again, that speaks to the generative model perspective. So, yeah.
I guess I have a question for Yejin, actually. So in the first panel discussion and the talks in the first session, the issue of embodied cognition came up a lot, right? And we know that in the brain, language areas like Broca's area and Wernicke's area, they talk in a very strongly coupled way with other parts of the brain that both represent and drive action in the world. But you've gotten a lot of mileage out of discovering good causal representations and knowledge representations just from language alone, or language plus static scenes. Do you think that we need embodiment to sort of create powerful AI systems, or do you think there's a lot more we can do without resorting to embodied systems?
Yeah, awesome question. Yes and no. So I didn't talk about it very much about my other grounded research, but that's how I studied, actually, thinking about common sense. I was thinking, I'm going to just extract knowledge from images. And then I realized that, wow, computer vision is really hard. I thought the language is hard, but computer vision is not only hard, it's also very slow. So after processing so much data, all that I got was like hundreds of knowledge. Then I'm an impatient person. So I wanted to go very large scale, very fast. And it seemed that language is going to allow me to go very large scale, very fast, covering a lot of broad scope of things. But I certainly do not believe that alone will be sufficient, especially for systems that might want to interact with the people through like robotic bodies or even computer vision, because you do need to somehow translate what you know about the world in language with like intuitive physics, the sort of stuff Joshua was showing earlier in his presentation. And that's really a huge missing link. And so that's why I think embodiment is important, but there's something really dissatisfying in the way that current language and vision research works, which tends to focus more on the sort of like conjunctive subset of concepts between what's in the image and what's in the language, as opposed to being able to really unify everything and then be able to learn everything in a more meaningful way. Another concern so I'm currently playing with 3D environment as one of the work in progress, but it's really frustrating how basically the world is defined by some engineers who built the 3D environment, and I cannot get out of it. And I don't know how the robust generalization will easily happen between that world and in the world that I presented in the images. Like, people might crash the car, or drown in the ocean. And I certainly do not need to experience any of that in the embodied environments in order to understand what it is like crashing the car or drowning in the water. So yeah, a lot more research to be done really, but I do like embodied research direction quite a bit.
Let me ask one last question. We'll go a couple of minutes over time since we started this session a little bit late, but this will be the last question, which actually I'm going to start with Yejin again, but I think it's one that other people can also have interest in. So I liked where Yejin began with sort of talking about Daniel Kahneman's System 1 and System 2. And I guess there's been a lot of talk about that. One of the most prominent recently was Yoshua Bengio at his Europe's 2019 keynote talked about System 1 and System 2. And I think a crude version of what you're meant to take away is deep learning has nailed System 1. And so now we can work on conquering System 2. Whereas you pointed out, there's somewhat more nuanced version where there are three things of perception, intuition, and reasoning. And so, well, maybe deep learning has nailed perception, but that then still leaves two things left. And, I was wondering what kind of models and methods we really have that are good for intuition, because some of the other things that were mentioned, such as probabilistic programming, that sounds a lot more like the reasoning level to me, and some of the other talk about sort of neurosymbolic architectures, the symbolic part is kind of on the seems like it's normally at the reasoning level. And well, what have we got for something like intuition? Well, Josh mentioned the metaphor of the game engine in your head, but I'm not quite sure that's really right for intuition. I mean, I was actually thinking of the example Josh gave of the Jenga game. I mean, I kind of think, whatever the flaws of your average game physics engine, I think it's 100 times better than my head is at working out the physics of what happens with Jenga blocks when they fall. But somehow I have enough vague intuition, I can play Jenga okay with my kids. So what should we be doing about intuition?
Yeah, that was such a nice summary, and it's true that I was opposing what Benjo said. But so what I realized about intuition as I read more into this non-CS Coxsci books is that, wow, there's so much going on in the intuitive level that humans are extremely powerful about. So I mean, probably don't you always also have this experience where you have an idea about new algorithm, but only intuitively that you have a hunch that this could work. You don't know why. You don't know why yet, but you just know, and you believe it very strongly. And then you look for some solutions to it. And then, eventually you do system to reasoning in order to figure everything out. But there's something really powerful about intuitive reasoning that even goes beyond the common sense type intuitive inferences. But today I was focusing more about the easier pieces, which seemed just simpler to target first. But other than admitting that I don't know the full answer to this, but this might be something really important to pay more attention to as an AI field, because this is really fascinating about human intelligence, and this might be something neural networks are very good at for some mysterious reasons.
Have ideas on what ways forward at the intuition level?
But I mean, we do need to
Can I raise a Coxsci perspective on this, and then just to frame the discussion? So cognitive scientists don't study intuition, and they don't, for the most part, really work on System 1 or System 2 either. Like those are, System 1 and System 2 is kind of a convenient summary of a whole bunch of different distinctions that is helpful for people outside of psychology to maybe understand, but it's not very helpful within psychology. Do you know what I mean? Like there's no part of the brain that's System 1 and part of the brain that's System 2. And there's many distinctions that are wrapped into that. And what individual people usually do is unpack those and study particular ones. And likewise, intuition is not just one thing. It's, maybe for people who are in AI or neuroscience, it would help to make an analogy to learning. Like if someone asks you, how does learning work in the brain? Well, there's so much that do you mean reinforcement learning? Do you mean classification learning? Do you mean learning at this time scale? Do you mean at this and that? There's so many things going on. But there are some things we can say about what I think the common sense intuitive notion of intuition is, and the ways cognitive scientists approach this, which fits with just what you were saying. So I might just put it out there, right? Which is like, often what we mean by intuition, I think, are unconscious computation. So we're not conscious of the computation or much of, which includes the representations and the algorithms, but something pokes into consciousness and it often has a kind of a probabilistic character. So we can have a strong intuition or a vague intuition. I can have intuition that that's right or that's wrong or that's good or that's bad, and I can't say why, right? So a lot of the things that we pack into the word intuition are of that sort. And I think actually, if you look over different areas of cognitive science and computational modeling, people have had success at capturing different things, different aspects of that with different tools, but they all come down to some kind of approximate probabilistic inference, or at least the ones I know. And that includes some, that's at least a way to render certain kinds of analogy models, because like Aude was talking about, sometimes there are analogies where it's like, I don't really know about this, but I think it's like that. So like high level similarity, where you can say, I think it is likely that what was true there might be true here. Or some of the Bayesian models that I used to work on earlier in my career, or like some of the neurosymbolic things, like when I was talking about Kevin Ellis's work there, or a lot of other work that people are doing in like neurosymbolic program synthesis, where you're basically, training a neural network to suggest, not to like write code, but the way we use it is it sort of guides a search. So it suggests to a search algorithm that's searching through this space of expressions in some programming language, where are the more or less promising ways to go based on the data that I've seen and maybe what I've done before. So
I agree that intuition is an imperfect word for the stuff in the middle.
But let's just say like approximate amortized probabilistic inference, basically.
I'm tempted to throw to Sanjeev and say, Sanjeev, when you have an intuition as to how to go about solving a problem, do you think you're doing approximate probabilistic reasoning in your brain?
Yeah,
I'm not quite sure that's.
I'm less interested in your intuition about how you do intuitive reasoning, but
I know we are running out of time, but if I may add a little bit. So I love a lot of what Joshi says, and I keep following his talk. But minor bits that I may not necessarily completely agree with here is that, so I don't know, like, I didn't read too many Kokusai books. In a year, there's a limit to how many you can take a look. But it seemed that this contrast between conscious and unconscious inferences is a thing that people do talk about a lot, even like maybe not for reasoning, but more for like, emotion-based research that focus just on emotion. They also seem to
or moral. You mentioned moral judgment.
Yeah,
a lot of those are also, yes.
We could just think intuition equals unconscious, a fast associative reasoning thing. That it seems that there have been such research, but
it's not always associative. I think it's. Yeah. It's usually may or may not.
So I agree with you that these things are very complicated in actual research, and these things are very much modeled up, and it's hard to separate that out. So that I totally agree with you.
Things that are fast and unconscious, but that can have a lot of computational structure.
About the probabilistic nature of it, I don't know if I can marginalize any of what I actually feel and assign, this is definitely an idea in which I can assign 0.81 versus 0.78. I really don't know.
The probabilities are approximate too. I mean, cognitive scientists
maybe we just know how to score things in a very inconsistent manner, though. I suspect we are very inconsistent.
So I wanted to ask one quick question. So intuition is being sort of equated with fast reasoning, but I think the more fascinating intuition for me, and probably everybody on this Zoom call got this at an early age, the subconscious thing, right? You're thinking about something, you sleep over it a night or two, and suddenly it's clear in your head. There's something else going on there.
Yeah, during sleep, you're dreaming about it. And then
but it's not just sleep. Also, just you go to the gym, whatever, right? Do other things.
Sometimes exercise can do it too, right? Like,
but all kinds of things, right? Play with your kids, whatever, right?
Yeah.
We could definitely talk a lot more about this, but I'm afraid I think we're out of time at this point and really have to move on to the final session, I'm afraid. So I'd like to thank all our speakers. It was a wonderful discussion. I think we could have done another 40 minutes of it, but unfortunately—
Thanks to you guys for a great day and great discussion.
So we can say thank you and goodbye to those speakers, and then we're going straight into the final short session where we're being joined by Bill Newsome and Michael Frank. Okay, I'd now like to open our final session of the day and to welcome two guests. First, I'd like to welcome Michael Frank, Professor of Human Biology and Director of the Symbolic Systems Program at Stanford. And then secondly, there's Bill Newsome, who is the director of the Stanford Wutsai Neuroscience Institute. Let me first of all start with you, Mike. Symbolic systems, that's a sort of strange Stanford thing. I know we're not unique. There is another university that has a symbolic systems program, but it's not such a common thing. So maybe you'd like to tell us about the symbolic systems program, and you better mention somewhere, how do you cope running a symbolic systems program in the middle of the neural revolution, I guess?
Well, yeah, thanks for having me. And I'm so glad that SimSys could be a co-sponsor to this really fun day of talks. Like you said, we're an undergraduate program at Stanford that's a fairly unique interdisciplinary mix. So we try to give students an education in computation, in formal methods, in philosophy, and in empirical cognitive science. So the idea is a student comes out of our program not only able to jump into building exciting new projects or participating in research kind of hands-on, but also able to understand the projects and the things they build in a broader theoretical and social context. So I'm hugely biased. I'm an alum of the SimSys program myself, actually. But I think we've got evidence for our success in this amazing broader list of alums, which includes founders from Silicon Valley companies like LinkedIn and Instagram, and also a wonderful list of academic alums doing research everywhere from neuroscience to philosophy and law.
Do you want to say a sentence more about how you think that comes together? Because, I mean, obviously the challenge in any interdisciplinary program is the students learn less about any particular thing than they could have if they had majored in psychology or majored in philosophy.
I mean, so one way of describing the major is Stanford's take on cognitive science, but honestly, I think that's not quite right. We call our introductory course Minds and Machines, and that's the really the guiding relationship that I think is at the core of SimSys. So it's all about these different relationships that you can put minds and machines in. How to use machines to understand minds, that's neuroscience and cognitive science. Minds and machines interacting, that's human-computer interaction. And of course, building machines with minds or that approximate minds as an artificial intelligence. So I guess I think of SimSys as a jumping off point for the ways that relationship between minds and machines can get construed and can lead to future research.
Well, thanks, Mike. And also to turn now to Bill, can you tell us a little bit about the Wutsai Neuroscience Institute and yourself? And
yeah, happy to, Surya. Like Michael, I'm thankful for the opportunity to be involved in this symposium today. It's been a really rich set of talks, and I regard both HAI and symbolic systems as wonderful partners here on this campus to neuroscience. Neuroscience has been praised at some points during the day today, and it's been denigrated at others. I believe that trash was a direct quote. So it's been fun to kind of sit on the sidelines, and I have lots of reactions. But I think that we have a lot of mutual agenda here, and I really look forward to working with HAI and with symbolic systems going forward. The Wutsai Neurosciences Institute was conceived about 8 or 9 years ago by a couple of guys named Hennessy and Etchemendy. I think most Stanford people are familiar with those names, our former president and provost, who thought that neuroscience is one of 2 scientific disciplines on campus that had the potential to create a campus-wide community of scholarship, ranging across multiple schools, multiple departments, multiple conceptual approaches. And I think they were very far-sighted in that respect. And so the WuXi Neurosciences Institute is campus-wide. It does not sit under any one school. It sits under the Dean of Research. And so I interact with deans and department chairs from all over the university. And that is because neuroscience is so inherently interdisciplinary. All of the subject material we have been talking about today is definitely highly related to neuroscience, and yet we could go talk with a non-overlapping group of people, which we will be doing tomorrow morning in a symposium on the neurobiology of disease, and it would be equally relevant to neuroscience. And we have contributions coming from applied physics at Surya's home department, from genetics, chemistry, statistics, engineering. And it's important for people to understand that this isn't just icing on the cake for neuroscience. This is bread and butter. This is the future of brain science. The brain is too big of a problem to be solved by any one discipline, any one set of experimental techniques, or any one set of concepts. And we've all got to come together and work in tandem with each other and energizing each other and educating each other in order to solve this problem. And that's what the Institute's about. It's about doing that. And we do that by investing in people, hiring faculty, creating interdisciplinary fellowships for postdocs, for graduate students. We do that by investing in research through our Big Ideas in Neuroscience internal granting program, along with some seed grants and a NeuroTranslate grant program, translating neuroscience ideas out into the real world. And we also do that through a new undergraduate education program that we started, a neuroscience interest group.
Thanks, Bill.
So we're in there, and we're doing this thing, and it's a natural ally to HAI and to SimSys both.
Yeah, thank you, Bill. And those remarks you've just said are really minimally a very good introduction to the next question I was hoping that people could address. But let me focus a bit more on linkages. That I think one of the feelings that we had in setting up HAI was that there was really a lot of connective tissue that needed to be developed to really get the synergies that we're hoping to see between research in neuroscience, cognitive science, psychology, and artificial intelligence. So let me maybe start with you, Mike. I mean, how do you see the prospects and the key things that we need for creating that type of connective tissue at Stanford? What are we doing, or what should we be doing? Perhaps, even, you focus quite a bit on the undergrads' interest in this space. What's the secret to connective tissue?
One little claim that I would make in response to Bill is that we're also kind of connected with HAI in our DNA, since John Etchemendy was actually one of the Symbolic Systems founders as well. But we're really working to expand that connection. So, for example, we just rolled out a new concentration, which is a specialization track in Symbolic Systems for human-centered artificial intelligence. The idea behind that is to guide students towards the intersections of AI, science, policy, and ethics that I think really characterize the HAI vision. So that's kind of one intersection. But more generally, I think where this comes together is in undergraduate research for symbolic systems. And talented undergraduates do an incredible amount to advance research. So one of the most fun things for me as a working scientist in the lab is to host undergrads in the lab over the summer, where they put their full attention on the problems that we're interested in and really make big contributions. And so with support from HAI and from WuXi this last summer, we actually had the biggest ever group of SimSys undergrads embedded in labs, getting full earnings replacement to be able to really devote themselves to research. And that's precisely the kind of experience that motivates folks to go to grad school. And one last kind of stop along the way before grad school is honors research, where we're really seeing this kind of integration happen already. So our Firestone Medal winner last year, Nyani Crawford, won a university level prize for work investigating face recognition in CNNs. Really this kind of very HAI topic of trying to understand the linkages between neuroscientific representations of face features and what's going on in the training data for networks. So I think we're really trying to build these links and getting students involved in research, getting them the tools they need to get kind of placed in labs early so that they can go on to do honors research and eventually to grad school is the track we want to encourage.
Great, thanks, Mike. Bill, I guess the same question for you. You're less of an undergraduate institute, more of a research institute. So I was wondering, how do you see the intersection between AI, cognitive science, and neuroscience going forward as a research field and through Wu Tsai? How do you see these fields working together?
Yeah, so we've given that quite some thought, Siri, as you know, because you've been part of the process. And we think that this interface is actually embodied. We embodied it in the design of our new building, the Stanford Neurosciences building here, which has a theory center inside it. And one of the principles here is that neuroscience going forward is going to go forward more rapidly and with deeper understanding and more incisive impact if theorists, data analytics specialists are embedded cheek by jowl with the experimental labs. It's important for both groups to work together, designing experiments, analyzing data. That theory center, when it is fully staffed, will have 6 research groups in it. Surya and Dan Yeamans will both be there, as well as Scott Linderman, a new hire in the statistics department. And I would say that research in that center and then filtering out to all of our experimental labs will involve theory, Surya being a classic theorist who really wants to identify general principles of operation and ideally that you can write down in closed form equations. But there are neural network people who are really impactful. Dan Yeamans being a classic person who's working hard with the deep convolutional networks. And there's high-level data analytics that are so important in neuroscience because we, like many other fields, are getting these floods of large, very sophisticated data sets coming into our field due to advances in technology. And traditionally trained neuroscientists like myself just is not prepared or competent to deal with these data sets. And Bob Laughlin, a physicist here at Stanford, once warned me, the biggest danger to your field is that 10 years down the line, you're going to have disks and disks and disks full of data, and you're simply going to be 10 years older. So the point being that understanding is really what we're after, right? And that's the goal of theory and computation and network modeling. And that's where we will have the closest interface with HAI going forward. And I would love to do, these interfaces have to be embodied in people. They have to be real embodied people. I'm all on the side of embodiment, by the way, in your previous discussion today. And hiring joint faculty, I think, is something that we really need to do. So these faculty will build the bridges. The students are already there. The students love this area, and they love the connection between neuroscience and artificial intelligence. And every faculty member we have hired is instantly glommed onto by a dozen students wanting to work in their labs. So the students are ahead of the institution at this point, and we need to do some hires together, to faculty level hires together, to create the environment where this can really go forward.
Let me continue a little bit along that theme and just see if there's any other items that people mention. So yeah, we've said quite a bit about the great programs, departments, and institutes at Stanford we already have. But there are always opportunities to build a more perfect union. And so Bill sort of mentioned the idea of how the students are already ahead and we just need to have the faculty there for them to work with. But for both of you, and maybe I'll start again with Mike, are there things you see as to how we could really do a little bit more to take things to the new level in really building the synergies between these 3 areas?
What I think is going to be a success here, but that hopefully we can replicate more. So one thing that is amazing that HAI has done as an institute is launched the Hoffman-Yeat program. So this is through the generosity of Reid Hoffman, who will claim as a SimSys alum here. So this kind of moonshot project is bringing together interdisciplinary teams and getting them to work together to try to accomplish really large-scale projects. So Dan Yeamans leads one of these teams, and Chris, your colleague, Chris Potts from Linguistics leads another that I'm involved in, where there's some synthesis students already starting to do some work. But that's kind of a, that starts with the moonshot, and that's an important thing. But creating a broader ecosystem of opportunities that brings faculty together, even when that's not the most convenient or easy thing to do, is really critical. So that kind of community building that brings the faculty together and maybe is also led and leads the students, as Bill was saying, towards this intersection is really what we need. So there's a combination of faculty and also opportunities for interaction, because the work of getting these conversations going is fun, but it's hard and it's not the first priority for a lot of folks, especially younger faculty. Right. So as we've seen in some of the discussions today, there are foundational issues that we disagree on. And so for each of the projects I've been involved in, you really have to have people sitting down again and again to hash out the vocabulary that allows them to have the interdisciplinary conversation. And sometimes you need people that are really trained in that conversation in order to be able to contribute. So creating those spaces is, I think, the next frontier for HI and for these affiliated programs.
Yeah, Bill, did you have any further thoughts you wanted to share on this particular issue of moving to the next level in terms of building connections? Or
yeah, I think really focusing for WuSci on the faculty level interactions is really important. I think that though, we have discussed Syria within the Institute, and I don't know how much this has been discussed within HI, that building interdisciplinary postdoctoral program would be a really good thing to do. I mean, Surya himself came out of string theory and physics for his PhD, and it was only as a postdoc that he got interested in biology and did a detour through yeast and biochemistry before winding up in neuroscience. But giving postdocs that extended kind of bi-disciplinary training and the freedom and time and money to explore a second area, I think, is a critical thing for us to develop the leadership of tomorrow, because tomorrow's leaders can't be somebody like me, who's a traditional neurophysiologist and I know how to do one thing well. But fortunately, I've been open to some good new ideas and having good collaborators. But the future really belongs to people who span these boundaries intellectually and practically and can speak the language already. I mean, as Chris or Mike, I think Mike was saying, having these conversations across disciplines is really hard. Just at the beginning, you're using the same words and you're meaning completely different things when you use those words. And just speaking a common language is so difficult. So the earlier we can start on that, the better.
Great. Well, Mike and Bill, you're not only program leaders, you're both also very accomplished scientists. So before the time runs out, I wondered if you have any thoughts or takeaways related to our theme and sessions today. So Mike, for you, earlier on, there was actually a cameo appearance of your SACAM project. And I guess by background, you're actually more of a developmental psychologist, but as things are going like this, you're either willingly or unwillingly sort of heading more in the direction of cognitive psychology, I think. What are your thoughts?
Because my interest is always in development and growth and change and learning, I was really fascinated by this morning discussion about sample complexity, about how much data it takes to learn something versus how much data it should take. And of course, right, if we want to trot out these examples, if you look at GPT-3, tremendous success by some, but not all measures, it takes 5 orders of magnitude more data than a 3-year-old. And I think it'd probably beat the 3-year-old on a lot of tasks, but my 7-year-old, which has got only about, she's got about double the data, is probably going to win on a lot of those. We heard a lot about interesting ways to improve transfer and efficiency today, but I guess my personal interest is in learning from other people. So, Chris, you mentioned scientists in the crib, and Josh talked about the child as hacker. I guess maybe I'm primed by undergraduate education, but I think about a slightly different metaphor, which is the scientist is actually the undergraduate student working in the lab. They do discover things. There are absolutely valuable discoveries that come out, but there's also a lot of coursework in reading, right? There are a lot of people around providing the scaffolding. And I think that's an important insight that I'd love to see talked about more. My colleague Hyo Gwon has really explored how many cases you can get kind of really rich information transferred by just a simple social situation that sets up kind of a very very subtle inference in a child. And that's the kind of inference that deep learning systems don't tend to make. A lot of AI systems are, you repeat the same thing over and over again, rather than inferring a tremendous amount from a single gaze or a single utterance. And so that kind of social learning, I think, is something that I'd love to see kind of integrated here.
That's a great point, and that's also one that I vibe with as someone who works with human language. I tend to feel like in a lot of discussions of both artificial and human learning, there's a real overemphasis on a single brain or a single computer, rather than thinking about the way that humans work collaboratively and gain so much from their interactions with other people.
And Bill, you mentioned you had some strong reactions to some of the neuroscience aspects of today. Do you have any takeaways you want to share?
I had a lot of reactions, Surya, many times together. It was fun. It was a very provoking set of talks and thoughts, so many. But I guess just the one that I would call out is I was really interested in sort of both what was similar and what was contrasting between the talks of Dan Yeamans and Chelsea Finn this morning. What was similar about them is that they're both interested in agents and agents interacting with an environment. But Dan is doing it virtually, simulating it in a computer. And Chelsea's actually doing it physically with robots, right? That actually move in the world and physically interact with things in the world. And I found my gut leaning more toward, that Chelsea's approach is probably going to, in the end, lead us to something more like animal intelligence than perhaps the digital simulations. And that's not to disrespect Dan's work at all. I admire his work tremendously. But there's something about interacting with the physical world, and I think that's what builds these physics engines, that Josh Tenenbaum was talking about at the end of the day. Chris, I even think it's relevant to the intuition point that you raised right at the end of the previous discussion, because if you really look at babies, a lot of interesting things were said about babies today. One of the most astounding things is their urge to move and their urge to interact with the environment. I mean, right from the get-go, right? First using that hand and then struggling to sit up and then wanting to stand up. And if you watch the baby, my mind goes back to J.J. Gibson. It's affordances. It is, when I touch that thing, what happens? Does it just stand there like a rock? Does it fall over? Which way does it fall over? And they're constantly experimenting with their bodies. And I think they're building premotor structures, Chris, in their brains, in motor, premotor cortex, that are being connected with sensation. So to say that AI maybe has solved perception, but now needs to work on intuition and whatever the other one was, I think that the connections between perception and action are far too deep to be segregated that nicely. So I think that was maybe the thing today that I had the strongest reaction to. And you can tell I'm a biologist because I want to see an organism in front of me, right? I want to see an actor. It's not just digital, zeros and ones out there in the world.
Yeah, I think that point of connecting perception and action is just a really important point that
yeah, I also agree.
I think we talk about at the start of the AI class, but very little of the work that's being done outside of certain areas of robotics like Chelsea's is actually doing it.
Yeah, no, I think it's super exciting. And also the way we design neuroscience experiments should deeply intertwine those. They shouldn't be separate fields in neuroscience. But anyways, it looks like this is all the time we have for today. I'd really like to thank you, Bill and Mike, for joining us here and for helping HAI as a co-sponsor of this important event. I'd also like to thank all our speakers for today for fantastic talks. To everybody out there in the world, we're going to make this entire broadcast available as a recording, which will be live following this event on our website, on our YouTube channel. Videos of each individual session will be available within the week. If you're on our high mailing list, or if you register for this event in advance, you'll receive a link as soon as that's available, as well as a survey. We'd love to hear from you about your thoughts about this event, about this field in general. Thank you for making the time to hear about this important research. Bill Newsom alluded to the fact that I was a string theorist before, so I used to study the physical world, but I shifted to this field. And I think this intertwined quest for both understanding biological intelligence and creating artificial intelligence may actually be one of the most exciting intellectual adventures of this century. Whereas, you know, physics was an extremely exciting intellectual adventure where we made a lot of progress. I think this is to me right now even more exciting. So have a great rest of the day, everyone, and thank you everybody for joining us.
Okay.